Okay, it's now 8. We're gonna wait for 2 to 3 minutes before we begin. Okay, the sound looks all right. Sounds okay. And to my American viewers, happy 4th of July. I wonder what happens if, say, 4th of July is on a Saturday. Do you guys still get an extra day off? Because if you don't, that would suck, no? We just had Canada Day. Yeah, I'm in Canada. So Canada Day, do you stream somewhere else? What do you mean? Well, I do stream on my 2.0 channel from time to time, but the main channel is where I mostly stream. So the 2.0 channel is for more experimental stuff. Okay, for example, the latest streams on the 2.0 channel is me self-studying abstract algebra from scratch. But right now, I don't know when I will be able to return to it because right now I have many requests and most of them are quite, how should I say, urgent. So this is my tentative streaming schedule. Hi, Vernon. Thank you so much for joining the stream. It's always nice to see you. So I was talking about my tentative schedule right now, streaming schedule at least, not video upload schedule. By the way, I just uploaded the first official complex variable episode. Okay, so the previous episode on complex analysis was more of a motivation. Yes, I can explain null spaces and column spaces shortly. Yeah. So I was talking about my tentative stream. I keep interrupting myself. Okay. Anyway, so right now the tentative streaming schedule is 3 times a week. I know it's, to be fair, perhaps it's a lot. And each stream is around 4 hours. And to be honest, I often go over time and approach 5 hours. So, and the topics are as follows. So first, on Tuesday 7 p.m., it will be the measure theory stream. I just had my first measure theory stream last Tuesday, which turned out, actually this Tuesday is still Saturday, so this Tuesday. So it turned out to be a big success, and we will continue on that. It seems like a lot of people are interested in measure theory, which was quite surprising to me. And Saturday is more flexible. Okay, so this very stream is requested by a viewer. Okay, so on Saturday I don't have a fixed topic. Okay, unlike Tuesday. So this week is linear algebra, and next week is mathematical finance. And I don't know what will be next, the week after next week, but we shall see. So, well, I tend to, I mean, if it basically is like this, if nobody requests anything, I'll just do my abstract algebra. But this Saturday stream, the one I'm streaming right now, is due to viewer request, and next Saturday's mathematical finance stream was also due to viewer request. Okay, and lastly we have a Sunday stream in the evening. So Saturday is in the morning for me, and Tuesday and Saturday are in the evening. This way, people around the world have a fair chance to catch them. So evening is more convenient for me. But I know it's not convenient for a lot of people. On Sunday, we do a two-part stream. First part is always mathematical statistics, a main feature of this channel, if I could say so. But ironically, I haven't uploaded a mathematical statistics video in a long time. We should fix that. And the second half of the Sunday stream would be on exterior ballistics. This is an interdisciplinary subject that fuses classical mechanics, differential equations, and numerical methods. But the main reason I decided to teach that subject is not primarily mathematical, but rather to drive home a point about the ethical responsibility of mathematicians or just science practitioners in general. Okay, so how do you view your work when it is, say, for example, can be used for destructive purposes? The main purpose is to encourage a self-reflection on that. Okay, so that's my streaming schedule basically, and I think I covered that. So right now it's 8:06. I'll just decide to give a quick overview of this stream. What are we doing today? So here we have two linear algebra problems, which don't seem to be too difficult, but things might look easier than they actually are. Okay, I just received these problems last night and I didn't have time to look through them, but we'll see what we can do. Okay, and of course we will go through the fundamentals. Okay, I'm not just going to solve the problem and leave it there. Okay, we'll go through the relevant definitions, perhaps results also, while we solve the problem. And to do so, we will use a reference, namely the good old Linear Algebra Done Right by Sheldon Axler. Okay, so we're going to use this as a reference. And so the idea is when we do the problem, the goal is never to solve the problem and leave it there, okay, like some sort of chore. No, the goal is always to enhance our understanding of the subject as a whole. Okay, so that's the goal here. Okay, and because we only have two problems, so chances are we'll still have some time, but maybe I got stuck, I don't know. Okay, just saying, if we still have time, we will look at another book. Okay, because we been only covering the theoretical aspect of linear algebra on this channel, which is unfortunate because I think not a whole lot of applied linear algebra courses or books have their fair publicity. So we're going to look at this one, Introduction to Applied Linear Algebra, and we're going to see what's so applied about it, right? Because in so many applied mathematics courses or books, applications tend to be treated as some sort of afterthought. You slog through all the proofs, and eventually you'll see a tiny little bit of application, which for me seems a little bit unsatisfying. But just so you know, these two authors, Boyd and Vandenberg, okay, so these two amazing people, they have hi Vizzy. So these two amazing people are well known for their contribution in the field of convex optimization. So if you are interested in machine learning, you know how important optimization in general is. But a huge class of optimization problems are convex optimization problems. So these two are mostly known in the applied math community for their contributions in convex optimization. And they decided to also publish a book on applied linear algebra. So we're very interested, at least I'm very interested, in seeing what they have to say. Vector matrices and least square. Okay, so that's the plan for today. So without further ado, let's get into the problems. Question 1. So question 1. In the questions below, I denote the imaginary unit. By the way, I just published the first video on applied complex variables, namely the definition of complex numbers, which somehow took 47 minutes to define complex numbers. Okay, I know I just destroyed my viewer count, but I don't care. It's an amazing topic, so if you enjoy it, I'm very glad. C is the set of all complex numbers. Also, AH stands for the conjugate transpose, also known as the Hermitian transpose, of the matrix A. A inverse is the inverse of A, of course. Okay, so just so you know, let's review the definition of conjugate transpose, shall we? So conjugate transpose, where's the, okay, AH is defined as AJI bar. Okay, so that's the transpose and then take conjugate, or conjugate and then transpose, doesn't matter. For A equals AIJ. Okay, for example, let's just say A is 1i 1 plus 2i minus 3i. Okay, so this is A, and AH is the conjugate transpose, so it works this way. Let's first do the actually. So you just turn the columns, or you turn the columns into rows and rows into columns, and then take the conjugate. So the first row should be the first column of A taking conjugate. 1 taking conjugate is 1. 1 plus 2i taking conjugate is 1 minus 2i. I taking conjugate is minus I. And minus 3i taking conjugate is 3i. All right, so that's AH. Okay, so just so we're clear about what this means. So when we discuss matrices with complex entries, we almost never use the regular transpose, and instead always use sorry, I just got disconnected. Okay, so yeah, I just got disconnected. I think now I'm back. But before I answer this question, before I walk through this question, let me just answer a viewer question. Unfortunately, I think I forgot to answer his question or her question soon enough that he or she might have walked away, which I'm sorry, but you can always check the recording later. Yeah, that's the question about null space. Chat disconnected? What the hell? Chat, okay, seems normal now. The question about null space and column space. So the definition is actually quite short. Oops, hang on, yeah. So the definition is actually quite short. Just irrelevant to this question. Let's say A is a, let's just use complex numbers. A is Cm times n. Yeah, I know Vizzy. Vizzy, you are here. A guy or a woman asked about the definition of a null space and column space, which I was talking about, the logistics and the stuff, and I didn't have time to answer. So here it is. The null space. Let me just say the four fundamental spaces, okay? So first of all, you have the null space. Null space is the set of X in Cn such that Ax equals 0. So that's the solution set of the linear system of equations Ax equals 0. That's the null space. And the column space of A, yes, Daga, DH equals D Daga in this question, yeah. Rigo is a physicist, so they write Daga. Okay. Anyway, same thing. Column space is the set of Ax. Okay, the set of Ax. So this is an image of the linear transformation Ax, where X can be any Cn. This is the column space. So why is it called the column space? Because it's the same as the span of the columns of A. The span of columns of A, okay? So that's the column space. And we also have two more so-called fundamental subspaces. One is called the left null space. The null space of A transpose, which, well, you don't even need to write a separate definition because that's just the definition of null space applied to A transpose. But let's write that anyway. It's the set of X in Cn, Cm. No worries, Rigo. A transpose X equals 0. And the row space of A transpose, the row space of A. The row space of A is the column space of A transpose, basically, which is defined as A transpose X, where X is in Cm. So these fundamental subspaces, so-called fundamental subspaces, were popularized by Gilbert string. Okay, so that's the definition of null space, column space, left null space, and row space. No, this is called left null space. Okay. Anyway, so that question is now answered. Let's go back to this question. So this problem has nothing to do with these fundamental subspaces, but they're important. Okay. So here we wish to show that D is a unitary matrix. So you just need the definition of unitary matrix. That's all, which we will review in Axler's book. Okay, so here we need the definition of unitary matrix. Now we will read it in Axler and we will write it ourselves. And second, if you have a G matrix that is defined this way, find the inverse of DH, GD. Okay, so we need the properties of inverses, but let's start with the unitary matrix definition. So this is linear algebra done right. Go to, I think, inner product spaces, but I'm not sure. Let's look at the index. Unitary spaces. Oh, sorry, not unitary space. Unitary matrices or operators. U. So while I'm flipping the pages, I'll just say unitary matrices are the complex version of orthogonal matrices. It says it is a unitary matrix if it's an invertible isometry. Okay, that's the original definition. Do we have a more computational definition? I think we do. Yeah, here. Exler uses the notation star, which is the same as H here, which is the same as dagger. Looks like a cross, okay, in Christianity. So you just need to verify this identity. S star S equals I. S star S equals I. And because S is a square matrix, you can just, yes, unitary inverse equals conjugate transpose. Exactly, you're right. Rigo, you're completely right. So yeah, you just need to verify the product of the conjugate transpose with the matrix itself is the identity matrix. So it's just a straightforward calculation. Okay, definition. You can treat that as a definition. Okay, definition. A in Cn times n is unitary if AHA equals AAH is I. Okay, so that's the definition, so it's very easy to check. The calculation is a straightforward matter, but let's just talk a little bit about why this is important. As mentioned in Exler, this represents a so-called isometry. So motivation. Okay, we're not just solving the problem, but also just a review of linear algebra. The motivation is as follows. So consider the map that takes x in Cn to AX. Okay, and let's suppose this map conserves or preserves the physics quantities, the physics version. Okay, preserves distance or preserves length. Suppose it preserves length, then what happened? Well, it just means x length equals ax length. Okay, I'm just being lazy and I write absolute value as length. Okay, there's no confusion here. This is just it's clear that it's a vector. Okay, so this is the same as the length squared. The square lengths are the same before and after the transformation. And of course, this is the same as x equals AXH. In the real matrices or real vectors, you just use transpose. Here we use conjugate transpose. Okay, and this is the same as x transpose x equals x AH AX. Okay. In this notation, x is a row vector, right? No, it's always a column vector unless we specify. So basically, if we write x is in Cn, this always means a row vector. Sorry, a column vector. A column vector. If it is a row vector, we would write x belongs to the dual space. Okay. Rn and Cn, they consist of column vectors. That's just a convention. Okay, so here all the vectors are column vectors. So this is, remember, your dot rows into columns. Exactly, your dot rows into column. You're right, that's the definition of dot product, or standard inner product. So what we have here is a quadratic form. The left hand side is a quadratic form in x, and the right hand side is also quadratic form in x. Actually, I missed an h. If they're the same function, then the matrices must be the same. So this is equivalent to AH A equals I. And it is a theorem for square matrices. If AH, if a matrix times another, let's say if a matrix B times a matrix A equals I, then immediately you have BA equals I as well. Okay, this only works for square matrices. But here, of course, we do have square matrices, so this is the same as AHA equals AAH equals I. Okay, and in general, of course, matrix multiplications are not commutative. This only works for square matrices. This only works for square matrices whose product is I. Okay, so that's the motivation for unitary matrices. So these are matrix representations of isometries as said in Axler. All right, so that's the definition, and you just need to calculate the product of D and DH. So this is D. Let's copy that. So let's just chill a little bit and do some matrix multiplication. Okay. Always doing proofs can be exhausting. It's fun, but can be exhausting. Right. If X is column vector, is AX the linear combination of all columns of A? Absolutely right. The top coder, you're completely right. That's why the column space is defined as such. AX is precisely, if the product AX makes sense. If the product AX makes sense, then AX is a linear combination of the columns of A. Okay, so let's keep writing the matrix D. I minus 1 minus I. So that's the matrix D, 4 by 4 matrix. So there's that. A, solution. So this is D, and therefore DH, taking the conjugate transpose, is half. Okay, first row becomes the first column taking transpose. First row taking the transpose becomes the first column. It's just 1, 1, 1, 1 down there. I'm asking, to me, it does not look like it. Actually, sorry, top coder, I just gave the answer, but let's walk through it, okay? This is a side tangent. Why is not obvious? There are just so many ways to understand matrix multiplication. That's just quote unquote by Gilbert Strain. So if you look at A of X, okay, what is A transpose? So what's AH? AH is a conjugate transpose. You take the regular transpose, but now you're also taking the conjugate of the entries. It does not make any difference for real matrices, but it matters for matrices with complex entries. And you almost always use the Hermitian or conjugate transpose, namely AH, for complex matrices. For complex matrices, A transpose is almost never used. Okay. Anyway, so here AX is the span of the columns of A. Let's just write it that way, okay? So let's do a simple calculation, say A, B, C, D. And you have X1, X2. So the intuition is clear. Right, so using the rule, you get A x1 plus B x2 and CX1 plus DX2. This is, of course, x1 times AC plus x2 times BD, linear combinations of columns of A. So AX automatically lives in the span of A. So yeah, it's just a straightforward computation. Okay, and this matters. And this matters a lot in problems such as linear regression. Rigo said, I'm kind of flabbergasted that isometry in Hermitian transform wasn't really covered in all my coursework. I always knew it's a transpose whose column are orthogonal. Yeah, you're right. You're right. It's isometry, right? Yeah, it's isometry. So it's the same idea. Orthogonal matrices represent isometries in real Euclidean spaces, whereas unitary matrices represent isometries in a complex, aka Hermitian, inner product spaces. Okay, so anyway, let's come back to DH. The second column would be 1. Now, because you have a minus I, you flip it to I, taking the conjugate. Minus 1 does not change. That's a real. And finally, the last I becomes minus I, conjugate transpose. Third column of DH, 1, minus 1, 1, minus 1. These are all real, so do nothing. I wonder how many percent of uni teachers linear algebra use complex numbers. Seems rare in the math major. You must, I think most of them do. It's just that the majority of time you spend in the course are with real matrices. Perhaps it's easier to visualize, but really there's no good reason to do that, in my opinion. Okay, you can just start with complex numbers from day one. Complex numbers actually make things a lot easier. You know, there's this, I think, purely psychological bottleneck for beginners is that somehow complex numbers are harder. Seriously, the computation is harder because you now have two components to worry about, but seriously, complex numbers are so much nicer mathematically compared to real numbers. Even in algebra, right? If you're working with complex matrices, you always have a full set of eigenvalues, right? So yeah, how nice is that, right? You don't have to worry about, oh, a polynomial has no real root. So the complex number is actually much nicer for linear algebra. Anyway, let's stop the rant and continue. The last row, 1i minus 1 minus I gets transposed and conjugated. You get 1 minus I minus 1 and I. Okay. Christian, I was taught in using real numbers. Generalization is pretty straightforward. Yeah, exactly. But even though the algorithms are mostly the same, the mathematical properties are so much easier, right? Because you have a full set of eigenvalues. You don't need to worry about things like, oh, the rotation matrix has no eigenvalue. Yeah, so of course it becomes harder to visualize things, but still you can reduce things to the real case and then draw a picture. Okay, so let's do the multiplication. Okay. So we're chilling here. DHD, but still be very careful with the computation. So DHD, we wish to check this is the identity. That's our goal. If this is verified, then D is unitary. So 1/2 times 1/2 gets 1/4. So let's put these two matrices side by side and do the calculation. Okay, so multiply matrices. Always a good time. First row on the left times the first column on the right, you get 4. Dot product. Get 4. Okay. First row on the left times second column on the right gives you 1 plus I minus 1 minus I. So that's a 0. As expected, you should get a 0. First row on the left, third column on the right, taking the dot product, we get 1 minus 1 plus 1 minus 1. So that's a 0 again. That's good. We want it to be 0. Okay. Okay. So first row on the left, fourth row on the right. Taking multiplication, you get 1 minus I minus 1 and then plus I. So that's a 0 again. Okay. 1, so starting from the second row on the left, multiply that with the first column on the right. 1 minus I minus 1 plus I, that's a 0. Okay. Second row on the left times second column on the right. You get 1 minus I squared, so that's a plus 1. And minus 1 times minus 1, that's a plus 1 too. And finally, minus I squared, that's a plus 1 also, so you get a 4. I still kind of struggle when questions show that, prove that basically such type of question asks me to reach goal by using logical step. You gotta know your definitions, right? So even though this question is it's just a straightforward computation if you know the definition of unitary matrices. Okay. Yeah. So the thing with advanced mathematics is that everything is interpreted literally. There's no interpretation by the way. Everything is taken literally. All the terminologies has a specific meaning. So if you don't know where to start, it probably means you don't know the definition very well. Okay. 1 times so second row on the left times the third column on the right, you have 1 plus I minus 1 and minus I, so that's a 0. Second row on the left times the fourth column on the right, you get 1, that's a I squared, so minus 1, and then plus 1, and then plus I squared, so that's a minus 1, that's a 0. Yes, exactly. Yeah, Vizzy, I was talking about this frustration last stream in the beginning. I was saying progress in mathematics is rarely linear. Okay, it's not proportional to the amount of time you spend. It's typically it starts very, very slow for some time, and then suddenly you snap. You just jump from, it's like a Heaviside step function. Understanding goes from 0 to 1. But you got to be patient to reach that moment. A lot of people give up before their aha moment came up. So that's why I call mathematics a test of character. It's a test for your stamina, basically. Okay, so I will not repeat the detailed calculations, but basically you should have these for the rest of the entries. Yeah, so basically what I was saying is, this, by the way, is not my opinion. This is not my opinion. It is the experience of pretty much all the mathematicians. So I'm going off a side tangent, but if you guys know the guy who proved Fermat's last theorem, Sir Andrew Wiles, what he said is, doing mathematics is like entering a dark room. Entering a dark room, and you just keep finding yourself stumbling into furnitures. You don't know what the configuration of the room is, so you keep stumbling into furnitures. But after a certain time, you would have a rough idea of what each furniture is located. But still, the room is dark. But until one day, you find the switch, and now everything is clear. So that's the 0 to 1 moment I was talking about. So Sir Andrew Wiles was saying you do that for 6 months until you finally found that switch, and then you enter a new room, and then stuck there for the next 6 months. So that's the yeah. So Riggle was saying might be worth mentioning the fold the transform along the diagonal trick, usually spot check for Hermitian. Yes. Yeah, so this is exactly, you're completely right. So it's almost the same as the trick for identifying symmetric matrices. Right? Hermitian matrices, by the way, Hermitian matrices, it's not used here, but Hermitian matrices are defined as AH equals A. Okay, AH equals A. So that's the definition of Hermitian matrices. So these are the self-adjoint operators for they represent the self-adjoint operators for complex inner product spaces. Okay, very nice tip. So question 2, derive the inverse, right, basically calculate the inverse of DHGD. Okay, so G is a diagonal matrix. But for diagonal matrices, the inverses are particularly simple. Notice G is diagonal, so we can just write DHGD inverse. Well, generally speaking, when you take the inverse of a product, you should reverse the order. By that I mean you put the last matrix inside the bracket and put it in the first one, and then put an inverse here. Okay, like so. This is very intuitive because you can think of a product of matrices as a sequence of transformation. Right? So now if you wish to undo all these transformations, you undo the last one you apply. So DH is the last one you apply. So here, in order to undo all of them, you first undo DH. Okay, and of course DH is very simple. Since DH, what's DH? Well, DH, we just verified that DH is the inverse of D. So DH inverse is just D itself. Okay, so part B. What we're saying is note G is diagonal, so its inverse is easy to calculate. DHG D inverse is D inverse times G inverse times DH inverse. Right. G is diagonal, D is unitary, and therefore D inverse is just DH. Okay, and DH inverse is D. So D inverse is DH, G inverse is easy, DH inverse is just D. Where permanently I'm going wrong when solving a problem. Yes, that's very common, right? That's very common. So if this is actually a lot of mathematicians were struggling with. Sometimes you don't even know where you got wrong. So it's nice to have a community and share your thoughts. But still, in general, I would say it's especially at the graduate level. I mean, in linear algebra level, I suppose people undergraduate linear algebra level people are still more likely to give you insightful response. But if you go to, say, graduate level where people are more specialized, it's very difficult to get feedback. Yeah. So basically that's it. So you just do the calculation. It's quite tedious, so I think I'll just leave it there. Okay. This is not a good advice for beginners. Okay, you don't just don't stop with the calculation because it's tedious. Okay, the calculation step is where insights are gained. So even though it looks kind of boring, I still recommend you actually do the calculations instead of using the calculator. G inverse, okay, G inverse, you just take the reciprocal of the diagonals. The inverse of 1 is 1. The inverse of I is minus I, because I squared is minus 1. I squared is minus 1, so I times minus I is 1. That's a minus I. Yeah, persevere and you will get it. It's tough, but don't give up. Exactly. So that's why, as I always say, math is like a test for your character. I mean, it's not saying like if you are not good at math then you're a terrible person. That's not what I mean, okay? Um, what I mean is it's perfectly okay to have other priorities in life. It is perfectly okay to have other priorities in life. Like, for example, you can't sit at the desk because you have sick family members to take care of. That's perfectly okay. Okay, so it's not an academic obsession at all costs. That's not what I'm trying to advocate. What I'm arguing against is that this popular cliche of, oh, I'm not a math person. In my opinion, that's just BS. Okay, that's a lazy way to absolve yourself from trying. Okay, so that's what it is. Not a math person. Maybe a hot take is a way to say, oh, I lost the genetic lottery, so I can't do it. So that's, in my opinion, completely false. Most people, they have perfectly adequate intelligence to study advanced mathematics, even at graduate levels. Okay, it's perfectly okay if you have other priorities. Okay, but don't say you're not a math person. It's an absolute fallacy. Okay. Anyway, unless you have a doctor's note, in which case, I mean, I'm not a medical professional, so I refrain from commenting on that. Okay, so that's this question done. The rest should be pretty mechanical and already show how to do matrix multiplication, so I'll just leave it here. Okay, so the next question. Okay, question 2. So question 2 seems a little bit longer, huh? And don't have much concrete numbers, unlike the question 1. Question 2 says, suppose that an n-dimensional vector space, it didn't say it's a real or a complex vector space. It probably does not matter, but just keep that in mind. I have one friend who did lose that lottery. That's but such a statistical anomaly I wasn't worried about. Yeah, I was talking about the 95% confidence interval. Okay, I know, like, if you have a congenital disorder or disease, I guess it's still possible. But I'm talking about, I'm 95% sure that whenever somebody utters the phrase, I'm not a math person, that's an excuse. Okay, with all due respect, that's an excuse. Okay. Anyway, so here, let's read the premises of question 2. I was saying the vector space V is finite dimensional, but we don't know the underlying scalar. So just keep that in mind. It might not matter, but still, it might matter. The underlying scalar sometimes can change how the vector space behaves. Is the direct sum. So we need to review this notion called direct sum. This is very important. The direct sum of two subspaces W1 and W2. Okay, when the vector x in V is decomposed as the sum of x1 plus x2, where x1 is in W1 and x2 is in W2. We consider the linear transformation that maps x to x1. Okay, let's just stop here for a moment, because to understand the second sentence, you really need to understand direct sum. So what is direct sum in a nutshell? The direct sum is just decompose a vector into components in high school physics. So we know how it works. So let's say in high school you have a vector, and perhaps you have a direction of interest. You can decompose that vector into that direction. But sometimes the two directions, by the way, you don't just always have one direction of interest. Perhaps you have two, and they are not necessarily orthogonal, and that's totally okay. You can still do a vector decomposition that way. Right? So the moral of the story is every vector in the plane can be decomposed into components along those two directions. So it's just decomposition of forces, velocities, all those good stuff. Every vector can do this. And mathematically, we say that the plane is the direct sum of those two lines. Right, so that's basically, yes, we can all be Euler, yeah, that's for sure. Because, yeah, what I'm trying to say is, you can still pick up a great deal, right? It's, of course, individual capability and time commitment varies. Okay, but still, I'm trying to talk about unused potential here, or wasted potential, or sometimes willfully so, right? So that's what I'm trying to get to. When Ming does stream like this, problem solving is very beneficial for me because I get to know people in the math community. Thank you very much, Vizzy. Yes, so yeah, I strongly recommend you guys come to the Discord server and communicate directly there, because here you have a live stream chat, right? But what if I'm not streaming? You can talk to people in the community that way. So let's look at the rigorous definition of a direct sum. And I think it should be pretty early part, in the pretty early part of Axler. Perhaps in subspaces? Subspaces, okay. Yeah, I think I found it. Sum of subspaces. First, we define the notion of sum. And then we define the notion of direct sum. Okay, so first let's look at the notion of a sum. What do we mean by sum of subspaces? Suppose V1 all the way to Vm are subspaces of V. I feel called out wasted potential. No, I mean, this is, okay, I don't know, okay, the whole perspective is very introspective, okay, you don't need to admit guilt to anybody or anything, that's not the point, okay, because I'm so interested in introspective criteria, that external standards can sometimes feel superficial. Is Ron Larson's elementary linear algebra good? Pretty good. Okay, so here we have the definition of subspaces. Suppose V1 all the way to Vm are subspaces of V. The sum of V1 all the way to Vm, denoted as V1 plus ... all the way to Vm, is the set of all possible sums of elements of V1 and Vm. I don't know. It's pointless to do this sort of optimization. If you're a beginner, chances are you will find them equally helpful. Okay. Anyway, so here we have the definition of a vector space sum, namely subspace sum. Is important. The definition is very straightforward. The sum of V1, big V1 all the way to big Vm equals the sum, equals the set of all the vectors that is of the form little v1 plus all the way to little vm, such that little v1 comes from big V1, little vm comes from big Vm. So that was what I was talking about, right? So imagine this is your origin, and you have two subspaces. This is V1 and V2. And you just take arbitrary vectors in each subspace and form a sum. And the collection of all such sums is called the sum of subspaces. This should be pretty intuitive. Okay, so that's the synthesis position. The synthesis process. Synthesis, what we call this is a synthesis. You are taking components I'm taking vector components and form the vector. I'm using the sense. I'm using I'm using the word component in the sense of physics. So you have a V1 component, a V2 component. But sometimes we also wish to do decomposition, right? Suppose you have a vector on the plane and you want to know the components of the vector along the direction V1 and V2. This is where we need the notion of a direct sum. Here, direct sum. The direct sum, which is O plus symbol, is denoted as O plus symbol. Suppose we have V1 all the way to Vm are subspaces of V. We shouldn't worry about DMC extraction or mass content, but we do. Yeah, exactly. That's why we're very careful. I'm being very careful about using what book I can stream and whatnot. Greetings from Persia, Iran. Hi. Greetings from Canada. Here we have the definition of direct sum. The sum, V1 all the way to Vm, is called a direct sum if each element of V1 plus all the way to Vm can be written in only one way. Yeah, so it's get only one way as the sum of V1 plus little v1 plus all the way to little vm, where each vk is in big Vk. So what does this mean? So we want to have unique decomposition. Here in the picture, it is intuitive that a general vector, say x, can be decomposed into the space v1 and v2 uniquely. That's the parallelogram law. Right? So it begs the question, when can this fail to happen? Well, if the two lines v1 and v2 coincide, then you would have no way to determine the components from v1 to v2. So that's an extreme scenario where you have two identical subspaces. Of course, in that case, you don't have unique decomposition. You cannot tell which component is from which space because you cannot even tell which space is which. A slightly less trivial case would be as follows. The intersection of two planes. The intersection of two planes. Say, this is now our v1 and v2. So the origin, of course. v1 and v2. And of course, v1 plus v2, that is the collection of all the vector sums whose summand are from v1 and v2 respectively. This is just R3, right? This is just R3. So imagine the ambient space is R3. This is just R3. But we cannot decompose uniquely into v1 and v2. Because it's easy to draw pictures. Say, you can have a vector like this. This is one way to decompose this vector. See, one from v1, another from v2. But you can also shift things a little bit. And get another equally valid decomposition. So here you have non-uniqueness. So in this case, even though v1 plus v2 is R3, this is not a direct sum. You cannot write v1 O plus v2 equals R3. Okay, so direct sum, here we have v is a direct sum of w1 plus w2. So in notation, v equals w1 plus w2, O plus w2. So in this assumption, we already assume whenever you have a vector x in big V, you can write x equals x1 plus x2 uniquely. This is a unique decomposition thanks to the direct sum. Follows straight from the definition. This is unique representation, unique decomposition or unique representation. Okay, and we emphasize that this decomposition has nothing to do with orthogonality. W1 and W2 don't have to be orthogonal. In fact, orthogonality might not even make sense here because we don't have a notion of inner product space. This is very general. So we assume that W1, a direct sum with W2 is V. Then immediately the second sentence makes sense because, the second sentence should have the extra implication that this decomposition not only exists but is also unique. Yeah. Riggle says, is it fair to say that the direct sum symbol is effectively serving additional given? It shows up in the added space given the, exactly. That's an extra assumption. So whenever you write, say, V equals W1 direct sum W2, you immediately know. Okay, even so, without the circle, if it's just plus, then of course we have this, but we don't know whether the decomposition is unique. If you put O plus, then the decomposition must be unique. This is just baked into the definition. Right? Yeah. So, Riggle, you're completely right. Okay. So we consider the linear transformation that maps x to x1. This is only a well-defined linear transformation because of the unique decomposition. If you don't have unique decomposition, then x1 is ambiguous. So that's not a well-defined function. Okay, so this sentence here, actually, we consider the linear transformation that maps from x to x1. This sentence makes sense only because of the direct sum assumption. Okay, so let's just use a picture to visualize what we read so far. So you have, say, this is W1 and this is W2. Okay, and let's say this is x. X can be uniquely decomposed into x1 and x2. Okay, so that's the two components. X maps to x1 is a linear transformation. Let B denotes the matrix of the linear transformation with respect to some basis. With respect to some basis, we don't know what basis is. Answer the following questions. The linear transformation, I think the linear transformation refers to this projection map. Okay, so why don't we give it a name? Denote. Let's use a different color. I tend to use black color for the actual solution, 1. Okay, denote. P, should say P1. P1 is a linear transformation from V to W1, and it maps x to x1, where x equals x1 plus x2, x1 comes from W1, and x2 comes from W2. Okay, let's call this star. The decomposition star is unique since V is the direct sum of W1 plus W2. The decomposition is unique. It's baked into the definition of direct sum. Okay, and thus P is a well-defined operation. Bye, Christian. Thank you very much for joining the stream. And thus P is well-defined. Otherwise, if x1 is not unique, then the P1 is not a well-defined operation. All right. So let's see. 1. Derive the matrix of the linear transformation that maps x to x2 with respect to the basis mentioned above. Well, what's the map? First of all, forget about the matrix so far. What's the linear transformation that maps x to x2? Well, it's just identity minus P1, huh? That's it. Then I minus P1 from V to W2 is exactly x minus x2. X not minus, x maps to x2. Where I is the identity matrix, or not identity matrix, where I is the identity map. Because if you want to get x2, x2 is just x minus x1. And what's x1? x1 is p1x. So this is just I minus p1 of x. So x2 equals I minus p1 of x. Therefore, this is a map. Right? This is a map that takes x to x2. So therefore, the matrix. Right, so let's write the assumption. Since B is the matrix representation of P1 relative to some basis relative to a basis in the premise relative to a basis, then I minus B, in fact IN, let's write IN because that's the dimension of V, right? Dimension of V. So the M by N identity matrix, IN minus B is the matrix of P2. This is the matrix of I minus P1. This is, which is the linear map. The linear map that takes x to x2. So we're done. That's the answer. So no calculation needed. It's literally just the definition of direct sum. Mathematical endeavors. I'm so happy to have come upon this. I love the quote from Benedict Gross on it being impossible to learn too much linear algebra. Yes, exactly. Maybe a little bit off topic. Maybe well-defined here as a discrete mathematical, like says here. Yeah, the notion of well-definedness is as follows. Okay, here I'm talking about the well-definedness of the linear map P1. Okay, the well-definedness is a context-dependent object. It's a context-dependent object, but basically, here what I mean is because the decomposition is unique, we can say x to x1 is a function. Remember the definition of a function or a map. For each element in the domain, the image must be unique. Right? That's the definition of function. And because of the direct sum, x1 is unique, and therefore the map x to x1 is well defined. This is what I mean. Okay. It really is not something that is specific to a particular field, say discrete mathematics and set theory. It really has to do with what are you trying to define, right? Here I'm saying we're trying to define a function. So what makes a function well defined? Well, its output for a given input must be unambiguous. That's what it means. Okay, so here that's part one. Part two, show that b squared equals b hold. Once again, it's perhaps easier to just think about the linear map, the linear transformation instead of the matrix. B is what? B is the matrix of P1 relative to a basis, an arbitrary basis. Arbitrary but now given basis. So if we can show P1 squared equals P1, then the question is done. So we say suffices to show So it's actually a good strategy. Whenever a matrix problem gets complicated or difficult to approach, you might want to think about what the linear map it represents. What linear map it represents. So that's the idea. Okay. So, in philosophy, you have this distinguished, so this difference between the so-called thing in itself, the thing in itself, and your perception of it, right? So it's in mathematics, this translates to the notion of an invariant, something that is coordinate independent. Also in physics as well. It's a hugely important topic in physics. The whole purpose of tensor analysis. When it comes to actual calculations, you often need bases, you need coordinates. But usually what we're interested in are things that aren't relevant to, that aren't dependent on coordinate system. So here, B is a coordinate dependent or basis dependent object. It literally says relative to some basis. So if we can just directly work with the linear transformation, then the result about matrices immediately hold. Okay, so let's work directly with the linear map P1. Can we say something about P1? Well, let's think about what's P1 squared. Can we talk about what's P1 squared? So, well, P1 squared, let x, it's better to work with the element. Let x, b, and v be arbitrary. So P1 squared of x is, of course, P1 and then P1 of x. But P1 of x is x1. So this is what we have so far. Okay. Actually, you know what? I'm trying to say is we need to show what? We need to show here. Suffices to show this. We need to show for every x in V, P1 squared is P1. Project to some basis and do it again. Exactly. You're absolutely right. If you project to some basis and then you project it again, the result doesn't change. This is pretty much linear regression in a nutshell. But in linear regression, you do it orthogonally. Okay. P1 of x1 is x1. Exactly, you're completely right. The top quarter, you're right. So I'm just trying to say, suffices to show P1 squared equals P1, and we need to show for every x in V, P1 squared x is P1 squared x is P1x. That's what we need to show. So to do that, let x be in V be arbitrary and now fixed, and let's calculate P1 squared x. P1 squared x is this. Right? Excellent intuition, but to do the proof, we need to be more formal, right? And what's P1x? Well, P1x is just x1, huh? P1x is just x1. And P1x is just x1, as we just said. Okay, so we need to show those two are equal. Basically, it needs to show P1x1 is just x1. So we need to show P1x1 is x1, and after that we're done. And let's use the definition of P1. So x1 is x1 plus 0. So the first x1 comes from W1. The 0 comes from W2. Since this and V is the direct sum, every vector in V has a unique decomposition of something from W1 plus something from W2. Right? So basically, you found one decomposition, and that has to be Z decomposition by the uniqueness of decomposition. The uniqueness of decomposition, P of x1 is just x1, as needed. Hi, Ange. Thank you very much. Thank you very much for joining the stream. So as needed. So we're done. P1 x1 is x1. And hence P1 square x is P1x. And this works for arbitrary x. So P1 squared is P1. And therefore, for matrices, you have B squared equals B. Okay? No calculation needed. Okay. So you can see the crucial step here, arguing P1 x1 equals x1, also boils down to the uniqueness of decomposition thanks to the direct sum. Part 3. Part 3, so show that P inverse times PB equals this matrix. This looks like a diagonal matrix. This looks like a diagonal matrix whose diagonal elements are either all 1 or 0. So how can that happen? So this holds for some non-singular matrix P of size n times n. Okay, so whenever you see P inverse PB, two things should come to mind. One, similar matrices, and two, eigenvalue problem. Okay, so it might be worthwhile to do a little review about this particular form. So where does that come from? So okay, it's a little bit difficult for me to reconstruct the theory from my head, but I know there's a good resource for that. It's my U-Waterloo Open Math. Okay, let's just, because it's difficult for me to reconstruct the theory from scratch and write everything, so let's just take a look at this exposition here. Inverses. Where's the change of coordinate matrices? You have, yeah, matrix similarities. First of all, we have matrix similarities. Let's take a look at this exposition. You don't have active version. What? Are you kidding me? Sorry. Okay, alternative format. Yeah. So here, what's going on? This is no. I'm talking about diagonalization. Star. Okay. Matrix of a linear map and similar matrices. The sum of a bunch of numbers in this format is 1 as a linear filter for the power. This is very advanced, but let's go back to the basics, shall we? The notion of the matrix of a linear map. So this is very basic, and it's very important as well. So imagine, let's try to do this more generally. Okay, so this is the starting point. Let L from Rn to Rn be a linear operator. You can swap Rn to n-dimensional vector space. Okay, it does not depend on any features of the real number. It works for any n-dimensional vector spaces. To define the matrix LB of L relative or respect to any basis B equals B1 all the way to Bn of Rn, we want to mimic what we have for the standard matrix. So what does this mean? We want the B coordinate. We want the B coordinate of vectors of Lx. Remember what this means. If you have a basis, then you can get a linear combination of an arbitrary vector in terms of the basis vector. And the coefficients of the linear combinations are called the coordinate vector. So you want the B coordinate vector of Lx to be equal to the matrix of L with respect to the basis B times the B coordinate of the vector x. So this is what we want. So this is the motivation to define LB. This is our motivation to define LB. Okay. So this is how it works. First, we write x as the basic expansion. We write x as a basic expansion, and the coefficients b1 all the way to bn is the B coordinate vector of x. Okay, so that's the B coordinate vector of x. And then we just use linearity. Let's calculate, or let's try to express Lx relative to B. The first step is just substitute the basic expansion of x. The second step uses the linearity of L. So L of B1 V1 plus all the way to Bn Vn equals B1 LV1 plus all the way to Bn LVn. And then you take the coordinate relative to B. You take the coordinate relevant to B. Taking coordinate is also a linear operation. Okay, taking the operation of taking coordinate relative to a basis, to a given basis, is also linear. So you can take out the Bn coefficient once again. So you see, the coefficients Bi's went through two operations. First, you can take them out of L due to the linearity of L. And after, you can also take out the square bracket B, because taking coordinates relative to a basis B is also linear. And now this looks like a matrix vector multiplication. Right? Somebody asked me that whether A times X is always a linear combination of columns. Here we're using that fact. Right? You see, this is a linear combination of column vectors. So to write it as a matrix multiplication, you simply put all those column vectors together into a matrix. So that's the matrix. And the coefficients in the linear combination together forms a column vector. And this is exactly what we wanted. Remember, B1 all the way to Bn, column vector, is xb. So this just tells us that LB is what? LB is this. This is LB. So this is the notion of linear transformation, the matrix of a linear transformation relative to a basis. Okay, this is the notion of the matrix of a linear transformation relative to a basis. How do you calculate it? You calculate the image of all the basis vectors. First, you calculate the image of all the basis vectors, and then express the basis vectors, express all those images in terms of the coordinates relative to B. Hey, Jen. Hey, I am X spider. Okay, yeah, this is what I was trying to say. This gives us a formula for calculating LB as follows. Definition. Your streams are great. Thank you very much. I tried to do my best here. If B1 equals if B equals V1 all the way to Vn is the basis for Rn. Once again, it doesn't have to be Rn. Okay, just an n-dimensional vector space will do. and L from Rn to Rn is a linear operator, then the matrix of L with respect to the basis B is defined to be the matrix whose columns are B coordinate vectors of the image of B under L. So this is a very long sentence. Very long sentence. So in terms of formula, this is how it works. You calculate the images LV1 all the way to LVN of all the basis vectors, and then compute the coordinates of each image relative to the basis B. So this is a column vector, this is a column vector. You should have n column vectors in with n numbers, and then put them together, get a square matrix. And this is defined solely for the purpose of having this formula. Okay, we wish to have this formula, so that we defined LB this way. Okay, so that's the definition of a matrix of a linear operator relative to a basis. Okay, here you have some computational examples. I will not go through them. But how does this have to do with similarity? Similar matrices. Okay, this is a similar matrix. Let L from Rn to Rn be a linear operator with standard matrix. So what do we mean by standard matrix? Well, standard matrix just means the matrix of the same linear operator relative to the standard basis. You know the standard basis 1, 0, 0, 0, 0, 1, 0, blah, blah, blah. That's the standard basis of Rn. Okay? But even though that's a common choice, there's nothing special to it. Okay? There's nothing special to a standard basis. Here, what we're going to discuss can work for any other matrix representation. Okay? It does not have to be a standard matrix. When we talk about standard matrix, we're implicitly using the standard basis. It can be any other basis. So let L be a linear operator with the standard matrix A. As I was saying, you can think of A as some matrix representation of L relative to some basis. Okay, and B be a basis. B, this is an explicit basis, or we specifically selected a basis. So here we have an implicit basis and an explicit basis. Here we begin by looking at how the B matrix of L is related to the standard matrix of L. So that's the whole motivation for similar matrices. Similar matrices are about relating different matrix representations of the same underlying operator. Okay, this is a very physical point of view. You have two reference frames, and you're looking at the same event. How do the coordinates transform? Right, so that's the underlying idea. It's the same idea. So the linear operator here is a common one. What changed is your basis. You change your basis from the standard basis to B. And of course, the numbers in the matrix representation in general will be different. But there's got to be some rule that relates them, right? Because they represent the same linear operator. So what is that rule? It turns out to be the definition of similarity. So let's look at the derivation here. Because this is the only way to understand mathematics. You want to have an a definition that is motivated. This way, the information aren't just passive, okay? Because if let's just say, I just tell you the definition here. Where's the definition of similar matrices? Next one, definition. If I just tell you, oh, this is the definition of similar matrices. This looks like a completely arbitrary rule. But let's just walk through the derivation and we'll see why this is defined and what this notion really says. What we're about to see is that if two matrices are similar, then they represent the same underlying linear operator in perhaps two different bases. So that's the idea. Okay, so let's see how the B matrix of L is related to the standard matrix of L. By definition of the B matrix of L, we have this formula. Right. So here, because A is the standard matrix, then L has a formula. L of x equals A times x. So here, A of V1 is just L of V1 in the definition here. Remember, in the definition for matrix representation, you have L of V1 relative to B1, right? Because here we stated that L has the standard matrix A. L of V1 is just A times V1, just matrix multiplication. All right? So there's that AV1 relative to B, blah, 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 all the way to AVN relative to B. This is the formula for LB. The formula for LB. So let's try to relate to the standard matrix A. Okay. Hopefully that can be written as a matrix product. That would be nice. Okay, so looks like we need to mention another subject called the change of coordinate matrix. So what is the change of coordinate matrix? By the way, let's read the full sentence. We want to compare this. We want to compare this matrix LB to the standard matrix. So we want to convert the B coordinates to standard coordinates. The standard coordinates, of course, refers to the coordinates of a vector relative to the standard basis. Okay, so this is also called the S coordinates in the textbook. We know that the change of coordinate matrix, oh, by the way, this is the notion, change of coordinate matrix, we'll review that in a second. So let's just read through this and we'll review the notion of a change of coordinate matrix. So basically, the change of coordinate matrix, as the name suggests, changes the coordinate, right, from one basis to another basis, or in language of physics, changes the coordinate from one reference frame to another. Okay, so this is the change of coordinate matrix. We'll see how it came up. Okay, but right now let's just use it to follow the rest of the derivation. Recall that the change of coordinate matrix is invertible. This is a fact, by the way, and this fact follows from two bases are both linearly independent. Right? Bases by definitions are linearly independent. So here, as a result of that, the change of coordinate matrix is always invertible. And in fact, every invertible matrix can serve as a change of coordinate matrix. Okay. So what it says is the B coordinates of x is P inverse x. Remember, the change of coordinate matrix from B coordinates to x coordinate is P. So P times the B coordinates, right? P left multiply the B coordinates of x gives you the S coordinates. And S coordinates, because it's a standard basis, is relative to the standard basis, is just numerically identical to x itself. So what I was saying is the change of matrix, change of coordinate matrix from B coordinates to the S coordinate is P. Therefore, P times xB is x. So you can write it as x coordinate of B equals P inverse x. It follows straight from the definition of change of coordinate matrix. Okay, so now we can write something finally. LB, we can do some derivations. LB, following from 1, is AV coordinate relative to B all the way to AVN coordinate relative to B. So that's an n by n matrix. Okay, and we know what the B coordinate can be written. How can the B coordinate be written? The B coordinate of x is P inverse x. So the B coordinate of AV is P inverse AV1. It just uses this formula, the second step. Right? Can everyone tell? AV1 relevant AV1 coordinate relative to B is P inverse AV1. And all the way we have P inverse AV1, P inverse AVN. Okay, that's the last column. And of course, by associativity, you have P inverse A together, right, times V1 all the way to P inverse A Vn. Right? Not much to talk about. But notice P inverse A is a common matrix in all the columns. So you can pull that out, and we get P inverse A times V1 all the way to Vn. Right? The matrix with columns V1 all the way to Vn. But what are these? Well, that's just P. But that's just P. Remember, V1 all the way to Vn are the basis vectors in B. And it is from the theory, okay, in the earlier part of this course, it is in the theory that the change of coordinate matrices from B to S is formed this way. Okay, we'll take a look at that after we finish here. So V1 all the way to Vn, matrix is B. So you can see how LB gives rise to the definition of similarity. Let's look at the definition. Let A and B be n by n matrices. Let A and B be n by n matrices. If there exists an invertible matrix P such that P inverse A P equals B. If there exists an invertible matrix P such that P inverse A P equals B, then A and B are said to be similar. Okay, so now we know what this notion of similarity is about. Two matrices are similar. Formally speaking, if there exists an invertible matrix P such that this equality holds. But geometrically, two matrices are similar if they represent the same underlying operator relative to perhaps different bases. Okay, that's the geometric intuition there. Okay, so this gives us a very the perfect vantage point to study eigenvalue and eigenvectors. Okay, once you have that, once you understand similarity, you're in the perfect position to study eigenvalue and eigenvectors. So let's go to the relevant section. Okay, so here eigenvalue, eigenvectors, yes, perfect. It's literally the second lesson, and it has quizzes too. So it's a good resource. I recommend this to everybody who are interested in basic linear algebra. So what we're trying to do is we wish to find a nice basis. We wish to find a nice basis so that a linear operator relative to that basis will have a matrix that is diagonal. We wish to do that. Given a linear operator, we wish to find a nice basis of the vector space so that the matrix relative to it is diagonal. Because diagonal matrices are easier to work with. And that's exactly, I know it's been a while since we looked at the question, and that's exactly what this problem is about. It says we wish to find a basis. We wish to find a basis of the vector space V so that the linear map for B1, the linear map for B, the linear map for B relative to that basis is diagonal. This is what we want. This is what we want. So for that, we just need to show you can its eigenvalues are either 0 or 1, right? Its eigenvalues are also 0. By the way, we haven't defined eigenvalues in our lesson here. Let's go with the lesson here. Okay. Let L be a linear operator on Rn. How do we even start looking for the special basis B when we don't even know it exists? Okay. We use a very good trick in math. We work in reverse. That is, we assume that there is a basis B, such that the B matrix of L is diagonal. And then we will use this to figure out what properties B must have. All right? So assume there is a nice basis, namely a basis such that the matrix of L with respect to B is diagonal. Right? We want that to happen. And let's write that as LB equals the diagonal of lambda 1 all the way to lambda n. Nice. Okay, so, well, we have our theory, right? We have our theory, LB. What is LB? In our previous lesson, LB is P inverse AP. So here we have P inverse AP equals the diagonal of P1 all the way to Pn. And that's exactly the question. See, P inverse BP is a diagonal matrix right here. That's the form. So we want that. And you don't need to actually get to the actual definition of eigenvalues and eigenvector, because this is already enough for the problem. Think about the geometry here. Think about the geometry here. B is projection onto the subspace W1. So if X is in W1, as Rigo mentioned earlier, if X is in W1, then P of X1 is just X1. It changes nothing. If it's already projected into the space where you want to project, it's the same. It's like when you lie on the ground, your shadow is always identical to your body. Right? It's the same length as your body. So the eigenvalue is 1 there. So basically what these 1s correspond to. What do these 1s correspond to? These are the eigenvalues. These are the eigenvalues of the linear operator P1, the projection linear operator, whose associated eigenvectors are just vectors in W1. Right, that's it. So that's it. So basically, if you have that, then you're done. You're done. So 3 suffices to show what? As we argued, suffices to show there exists a basis of, let's write it as B. B is already used. Oh, damn. Let's use beta. Okay, beta of V such that the matrix such that the matrix of, how should I put this? Because we still want to connect to the P, right? We want to, for some single, because to show this we actually need to give a description of P. Let's first work in the vector space without talking about matrices. Let's first work with that. First, suffice to show there exists a basis beta of V such that the matrix of P1 relative to beta is diagonal, whose entries are Actually, you know what? Let's first. No, I don't want to talk about matrices now. This is redundant. It, that P is different. Yes, yes. Well, because I was thinking about projection, right? P is P is kind of the standard notation in similarity. Yeah. P is different from the P here, which is a little bit confusing. You know what? Let's use a different letter. Okay. Let's use a different. You just happen to use P. Yeah, yeah. So let me just write big pi to avoid the confusion. Okay, big pi. Big pi here. Big pi here. Okay. I will change all the P1 to big pi 1. The top coder says P inverse LP says apply the linear operator in the standard basis and then bring the result back to your basis. Exactly. Exactly. That's a very nice way to describe things geometrically. So, yeah. Pi. I'm using big pi instead of P. This way, P is less overloaded. One of the main annoyances in probability is that P is everywhere. You know, P P is so overused in probability, and it sometimes gets annoying. Anyway, here let's change everything from big P1 to big pi 1. Because the question did not give a letter for that linear operator projection onto W1. Actually, you know what? Something I just thought about and would like to put it down as perhaps a homework. As perhaps a homework. So, yes. Okay. I'm thinking about a converse of 2. Proof. Suppose, okay, let start from the beginning. Proof. Actually, start from, let's say, proposition. Proposition. Let V be an n-dimensional vector space. Okay. Let P from V to V be linear. This is a linear operator. If P squared equals P, then it is a projection. Then P is a projection. Okay, that is, what do we mean by P is a projection? That is, there exists a subspace. There exists a subspace W. There exists actually subspaces. There exist subspaces W1, W2 such that for every x in big V, Px is in W1. And Actually, you know what? Let's add such that this is the first property, so that this is property 1, and 2, W1 direct sum W2 equals V. So this is like a converse of the theorem here. Sorry for the annoying erases, but it perhaps helps for 1 to 3 people who read the notes after the stream. Yeah, I will upload this, okay? Rico, I'll upload these notes for what it worth. Okay, so I was thinking about this proposition. So we started from the assumption that V is W1 direct sum W2, and Px is defined as actually this is perhaps not ideal. There exists okay, so let me just put that at the first one. I'll upload the notes as it is after I finish the stream. It will be in the form of a Google link. Thanks, PG. So, yeah, for every x in big V, Px equals x1. Let's use the same format as the original proposition. P of x equals x1. Where x equals x1 plus x2. X1 is from W1, x2 is from W2. That's the second proposition. The second property. So this is what we're trying to prove. And the rest is just explain what projection means. P is a projection. There exist subspaces W1, W2 of V such that the two properties hold. Sorry, didn't mean to assume. I thought you always did. It might be easier to ditch in Google and use Git on the PDF you do use. You mean GitHubs? Yeah, that would be a good idea. I mean, Google is actually I don't. I'll start a GitHub later, but right now I think most likely I'll be using Google for this one. Sorry, Rico. So yeah, that's the proposition. I mean, we'll come back to that. Let's just finish the last part. Suffice it to show there exists a basis beta of V such that beta, let's give the proof writing is nonlinear. Okay, you don't typically just start from the first line and go all the way to the last line. Typically, it takes some sort of reorganization. It's very common. Exist a basis, you just call it V1 all the way to Vk, Vk plus 1 all the way to Vn. There exists such a basis of big V such that PV1 equals V1 all the way to PVK. Actually, I changed the notation, did I? I used big pi. We use big pi. Okay, sorry. Big pi. Big pi 1 all the way to Vn not Vn, but Vk is Vk. So this is saying V1 all the way to Vk are eigenvectors of pi 1, whose associated eigenvalues are all 1. Okay? And pi 1 Vk plus 1 is 0, all the way to pi 1 Vn is 0. Okay, so this is, we say, okay, suffices to show that, but we want to explain why this is sufficient, and why does this relate to the invertible matrix B here? Why is this invertible matrix B here? So now we have to discuss the underlying basis for B. Otherwise, this cannot be done. So, to see why this is sufficient, we have to, how does this connect to P, right? Because showing this is easy. Because you just pick V1 all the way to Vk as the basis for W1, and that will do. Showing this is easy. But how do we connect to the matrix P? It shouldn't be too difficult, but it takes some extra notation. That is not spelled out in the main textbook. Okay. Now, not textbook, but the question, what I'm talking about. My goodness. Here, I'm trying to say is, let the underlying basis for B, for the matrix B, be, say, alpha. Of course, alpha is a set of vectors, set of n vectors in V. Let's just call them U1 all the way to UN. Underlying basis for B. That is IE, because remember, B is the matrix representation of pi 1. Namely, pi 1 relative to alpha is B. Okay, so that's the assumption here. And I think you just need the change of basis matrix to relate the two, to relate P and B. For that, let's look at some general theory again. I think it should be linear algebra 2 when we pretty much discuss the same thing but in abstract vector spaces. Okay, linear mapping. We have that matrix of linear mapping. Yeah, so here we're generalizing what we discussed into the setting of abstract vector spaces. You pretty much do the same thing, but with more notations. Here, if we have a linear mapping from two vector spaces V to W, from vector spaces V to another vector space W, and let's say you have B equals V1 all the way to Vn, being a basis for big V, and C being a basis for big W. Then you can define this matrix, which is CLB. Okay, CLB. CLB is defined as follows. Remember, now here in this setting, the domain and codomain are not necessarily the same, right? So, but the idea is the same. You first calculate the images of the bases in the domain. So you first calculate LV1 and LVN as usual. And now you calculate, and next, right after that, you calculate the coordinates of all those images. But what coordinate? Well, LV1s are all in W, so it only makes sense to calculate coordinates relative to a basis in W. So it's LV1 relative to C all the way to LVN relative to C. Okay, and this definition allows us to write LC coordinate relative to X is CLB times XB. So what this means is, if you take the B coordinate of your input, X, left multiply that vector by this matrix, CLB, you get the C coordinates. You get the C coordinates of the output, LX. Okay. Very similar to what we just did in Rn. Okay, and how do we relate, say one to another, huh? How do we relate one to another? For that, we need to review the change of, because I can't remember the formula. You see, still, it's worthwhile to always go back to linear algebra. You see, I always believe, if you can reconstruct the theory from scratch in your head, then there's room for improvement. Okay, let's just put it that way. I'm not going as far as saying, oh, you don't understand the subject. I'm saying there's still room for improvement. Change of, where's the change of basis, change of coordinates. So how do we do that? Yeah, so that's the formula. Right, if you have, if you have, say, a vector space V, I used to use the notation, F base in base R, that's the Axler's notation, Wendelin. Yeah, that's the Axler's notation, which well, to be honest, I'm not a huge fan because it looks just so long, man. It's exhausting. I know what you're talking about. The person, Wendelin said, hang on, linear math matrices, so this is what it looks like. It's so long. Here. Yeah. Almost there. That's Axler's notation. Did you guys use Axler for your course or something? Where the hell is it? Yeah, it's here. You see, that's the definition, right? The matrix of a linear map, right? Base in, base out. So that's the notation. But I mean, there seems to be a lack of standard notation for this particular concept. Yeah. So let me just, if you can bear with me, just stand this notation. I think it has a nice feature to it because it respects the order of multiplication. So in is, you see, basis in is on the right. This way, seems like the B's are attached to each other, C's are next to each other, if that makes sense. All right, so that's what the change of basis vector, change of coordinate vector does. Sorry, what's that? Well, change of coordinate matrix does. If you have a vector x and you have two bases b and c, transforming xb into xc is a simple matter. You just left multiply xb by the change of coordinate matrix from b coordinates to c coordinate. it is written as CPB. Okay. This is perhaps better expressed in terms of tensor notation. But for tensor notation, I mean tensor notation in physics, with the Einstein summation convention and all of those good stuff. But that will require indices. And mathematicians, generally speaking, dislike indices. All right. So what I was saying is that how can we construct that matrix P? How can we construct that matrix P? I need more space. This is because, oh no, my water is full of cat hair. It's disgusting. Sorry. This is because, can we write that in a nice way? Pi 1 relative to beta, right? Pi 1 relative to beta is, can we write it fiber? What do you mean fiber? As we said, this is pi 1 v1 pi 1 v1 relative to beta all the way to pi 1 vn. Cat hair. Oh, gross. I'm pretty sure that's not how fiber works. Anyway, so this is pi 1. That's the desired matrix. We wanted something like that. This is what we wanted. Factorization of vector space based on a factorization polynomial. Nulling the endomorphism here is too ahead for this question. Yeah, I guess you're right. Yeah, Wendell, you're right. You're absolutely right. But I'm trying to do things the elementary way. Because this question asks for this identity holds for some non-singular matrix. I'll try to do things explicitly and just give the form of that matrix. Yeah. Anyway, so here, that's big pi 1 relative to beta. Big pi 1 relative to beta. How do we connect big pi 1 relative to alpha, though? Remember, that's just the change of coordinate. This is played by the change of coordinate matrix. Remember, here in our theory, in Algebra 1, this is a similarity transformation. Hang on. Going back. No. Linear Algebra 1. This is what we did. Oh, sorry, not quiz. These are nice quiz questions, even though there is a drawback because it cannot grade proofs. It's still a good source of practice if you're a beginner. And it's interactive and all of that. So here, what we wanted is, where do we have this projection business going on? No, I don't want that. I want similarity. Yeah. The definition of similarity. So what is going on? How is the definition of similarity motivated? Well, a linear operator, right? A linear operator L relative to B, a basis B, have a matrix LB. LB is P inverse. You can call this LS, right? Because here L square bracket on its own is the matrix representation of L relative to the standard basis. So this is, let me just write it down. So this is from the U Waterloo Open Math. Diagonalization, linear algebra 1. Diagonalization section, similar matrices. What we had there is a derivation that says LB is P inverse LSP, right? And P is what? P is the change of coordinate matrix from B to S. Okay, so P is in fact P from B to S. So PB here, S here. Okay, that's P. So therefore we have LB equals P inverse. No, P inverse is, let's write it as SPB inverse LS, and then times P, which is SPB. Here in the original exposition, S is standard matrix, but we didn't use that assumption. So this works for any for all bases, S for all pairs of bases. Okay. S and B of bases. So this works in general. So how do we connect that? Well, here we have pi 1 and pi 1 alpha and pi 1 beta, right? So therefore, you can relate them using a change of basis matrix. So pi 1, let's just write pi 1 beta. Pi 1 beta is what? Is alpha P beta inverse. I'm just mimicking this form. I'm using S for alpha, obviously. L of, not L, but pi 1. Pi 1 of alpha times SPB. SPB, which is alpha P beta. Alpha P beta, okay? So that's the relation between the two. The left-hand side is already what we wanted. This is what we wanted. There, what's wanted in the question. And what is pi 1 alpha? Well, pi 1 alpha is B. Pi 1 alpha is B. So this is the P that we wanted. P in question. So P in question is a change of basis matrix. So therefore, the P matrix in the change of basis matrix is what? Is this change of basis matrix. If you can have beta, then P is immediate. It's just the change of basis matrix. But just for completeness, I'm going to write down the formula for the change of basis matrix as well. So this way things are super clear. Okay, let's go to the linear algebra module. So how do we define CPB? Well, the idea is similar to how the matrix representation of a linear map is defined. Hang on. Yeah, this is CPB. So you take the basis in the B vector. So you take the basis in the B basis, okay, V1 all the way to Vn, and then you calculate the coordinate relative to C. Okay, and this will guarantee that XB, the coordinates in B, left multiplied by the matrix CPB will give you the C coordinates. Okay, so let's just use that here. So how do we change the notation? Well, you just calculate the coordinates of the beta vectors, the vectors in beta, V1 all the way to Vn and all that, relative to the alpha basis. V1 relative to alpha, all the way to Vn relative to alpha. So that's an explicit formula. This is the explicit formula for P. So this shows existence completely. Okay, and I'm just going to here suffices to show a basis. This indeed exists. Take V1 and Vk be a basis of W1 to be a basis for W1, and Vk plus 1 all the way to Vn to be a basis for W2, and we're done. Because if it is in W1, then pi 1 acting on the vector will just give the same. Right? It doesn't change. If the vector is in W2, pi 1 acting on that gives 0. Exactly as needed. Right? So to summarize, how can this identity work? Well, you need to pick the P matrix correctly. And the P matrix is a change of coordinate matrix. It's a change of coordinate matrix from the basis beta to alpha. Alpha is the original basis where B is defined. Alpha is the original basis by which B, big matrix B, is defined. And the beta here is our special basis. Our special basis is defined as follows. The first K vectors are basis vectors for W1, and the rest are basis vectors for W2. Together, they form a basis for V. And you calculate the change of basis vector, you get what you needed in the question. So that's it for the question. Let's think about this proposition. Right? I just formulated the proposition here. Perhaps we need to refine it as we go along proving it. I think this should be true. Oops. I think this should be true. Basically, that's the converse of the question 2. Right? In the question, we assume that V is a direct sum of two subspaces, W1, W2, right? And define the projection onto W1, okay, which we denote as big pi 1. And big pi 1 has this crucial identity. Big pi 1, by the way, this is called, I think it's called idempotent. Okay, I think this is called idempotency. B is idempotent. Right, potent. And this is crucial in statistics because statistics, 90% of it is a matter of projection, as we keep hammering in the channel, right? 90% of statistics is some sort of projection. So idempotency is absolutely crucial here for statistics. So the question is, if we assume idempotency, can we infer, can we derive, right? Can we deduce that this is a projection? If we assume idempotency of an operator, then it has to be a projection. And here is our definition for a projection. Not an orthogonal projection, but a general projection. P is a projection means there exist subspaces W1, W2 of V such that V is the direct sum of W1, W2. And for every x in big V, Px equals x1, where x equals x1 plus x2 such that x1 is from W1 and x2 is from W2. So how can we, I think this is true, because I mean this is typically how math research is about, right? You postulate something and then you try to prove it. And not postulate, postulate means you don't need to prove it. I mean you conjecture, that's the correct verb here. You conjecture a proposition and you try to prove it. Sometimes you succeed, sometimes you don't, right? Such as life. So how do we even start by with the question? In fact, we have W1. Yeah, that's the thing, right? That's the thing. Kernel and image, exactly. And Wendelin, I think your fantastic idea is our starting point for proving this proof. Let's just take W1 to be the image, right? The image of P. And W2 to be the kernel. Okay? And we need to verify all of them. I think the difficult part is the direct sum, right? The second part should be easy. Once you have one, because so let's think about that. Let's we want to show that the direct sum of W1, W2 is V. For that, I think we need to use a result. Perhaps it's in Axler about direct sums. We want to use a result. I mean, we perhaps need to use a result from Axler. I'm not sure if it's even in there. Condition for a direct sum. Yeah, here's direct sum of two subspaces. Okay, so U plus W is a direct sum if and only if the intersection is 0. Okay, so let me just copy this down. Perhaps this is useful. Let's verify the intersection of image and kernel is 0. Can we do that? Claim image of P intersect the kernel of P is a 0 vector space. Proof. Okay, let say X is in the image of P and X is also in the kernel of P. So therefore, if X is in the image of P, then there exists or should we say X equals P times Y for some Y. In V. So that's the first assumption. And also you have X is in the kernel of P, so P of X is 0. So P of X is 0. So can we combine the two? Well, why don't we just substitute X equals Py to the second? So you have P of P times Py equals 0, so P squared Y is 0. So P squared Y is 0. But since we have P squared equals P, that's in the assumption. Since P squared equals P, Py is 0. So Py is 0, so X is 0. Therefore, X is 0. So therefore, if X is in the intersection, X must be 0. So indeed, you have as claimed. Actually, let's write that, therefore. So what we managed to prove is that the left-hand side is a subset of the right-hand side. But obviously, the right-hand side is a subset of the left-hand side because every vector space contains 0. So the reverse direction doesn't even need to be proved. As a result, the claim holds. So that's very nice. So that's very nice. We have the intersection being 0. And also we need to do another proposition. Namely, we need V equals the image of P plus. So that's just the ordinary sum. That's just the ordinary sum without mentioning the direct sum. If you have if you have intersection is 0 and V is the sum of the two, then, well, V is the direct sum. So can we do that? Well, you just need to take an arbitrary element in V and decompose into those two parts. And the picture is very suggestive here. So imagine this is the projection onto this line, X. This is the image of P. This is Px. Right, so you can just write proof. Let X in V. We have X equals Px plus X minus Px. Right, Px obviously is in the image of P. What about X minus Px? Is it in the kernel? Is it in the kernel? Well, one way to check, you just need to calculate P times X minus Px is 0. Indeed, this is 0 because this is Px minus P squared X is 0. So you're done. So second claim is done, and therefore, yeah, I think we have everything. Both 1 and 2. So the proposition is proved. Right? So that's interesting, right? So basically, together with what we have in question 2, so we can summarize a new result theorem. And let, or should we say just one word without notation, that would be better. A linear operator is a projection if and only if it is idempotent. If and only if it's idempotent. So that's pretty cool. Okay? And I think we're done with this problem set. Okay, if we're done with this problem set as promised, let's take a look at a book. Let's take a look at another book on linear algebra, which I'm very excited about. And I think I mentioned it in my Discord, but if I'm being honest, I didn't have a thorough overview of this book. But in my grad school career, I did spend some time, quite significant actually, studying the book by the same two authors on convex optimization. So I strongly suspect their undergraduate level books are also very nice. By the way, Boyd has full lectures on convex optimizations on YouTube. Okay, so in case you guys are interested, go check that out. Just search Boyd convex analysis on YouTube. You should be able to find the lectures. Let me just type that in chat. The hell? I can't type in chat? Come on, OBS. Yeah, okay, great. Boyd. Search. Boyd. Convex analysis, not analysis, convex optimization in YouTube. Okay, so let's take a look at this book. And this book, as it suggests in the subtitle, it has three parts: vector, matrices, and least squares. Okay, so here, let's go to, here you have vectors. And in the vector part, it talks about clustering, k-means algorithm, which is pretty cool. And matrices, that's the second part. Matrices. As you can see, the topics are very applied. See, for example, there's a separate chapter on linear dynamical systems. These are fantastic topics. This is a gold mine for making videos. Chapter 3, not chapter 3, but part 3 is least squares. And I can see there's already highly unique in the sea of linear algebra textbook, because there are things that usually most textbooks don't talk about, such as pseudo-inverses. Pseudo-inverses, for example, super important in statistics. And I think here, because the book is pretty long, it's 473 pages, more than half of that is on least squares, which is fantastic. I'm so glad this book exists. Okay, this looks extremely promising. How many people are still in the stream, by the way? 14. That's cool. So yeah, I was saying, like this book, I'm just trying to spot, for example, the non-standard topics here, as far as the linear algebra course is concerned. So as you can see, the author always have application in mind. It's not just an afterthought. In the first chapter, where vector is introduced, it talks about complexity of vector computations, like how many flops, meaning floating point operations needed for things like inner product. And regression model, it seems like every chapter has its own application, though, which is awesome. And clustering is already an application, and it has applications upon application. My goodness, this is a gold mine. Hi, Renzo. Thank you very much. How did you discover my channel, though? Is it a measure theory live stream? Renzo? Is this I suspect it's the measure theory live stream. Well, yeah, feel free to correct me because that live stream went better than much better than I expected. But yeah, feel free to let me know. Like every one of you, how do you guys discover my channel? Yeah, okay, I see. Because I always thought measure theory is such a dry and technical subject that only pure math and stat major needs it for the most part. Like not even all the applied math major needs that. I mean, I would say you can never say you never need it, right? So I'm just generalizing things. So basically, I was saying, okay, this is a pretty niche subject that only in math, not all math people necessarily need to take that. So it should be pretty niche, but turns out it blew up. It just by stream standard, it blew up. That's crazy. It's a 5 hour stream for goodness sake, and there's almost 10,000 people have watched it already. Like, just I'm not quite sure what's going on here, but yeah, this really. I mean, it's a good thing. Don't get me wrong. So, yeah, there's that. Okay. Thank you guys very much, as usual. Okay. So here, orthogonal vectors, Gram-Schmidt, these are standard stuff. Matrices, also complexity. I suppose this is complexity of matrix computation. This is amazing. My goodness. I'll have to say something about this, or perhaps make a video about it. But I don't know. Like I feel like I'm hesitant to make book review videos now. Because I feel like that is kind of saturated on YouTube. I'm not sure what you guys feel about it. I feel like book recommendations there's so many videos of them. You're suffering from option paralysis now, which is kind of a shame because I really wanted to talk about specific books. 10K? Yeah, that measure theory stream. Let me just check the stats. For such a subject, like, this is crazy. There are professors, university professors, who uploaded their measure theory lectures on YouTube that don't even have that many views over years. Like, it's not even a week. Like, that's crazy. So, here, well, it's not quite 10K, but it's 9.3 and it's still going strong. It's 9.3K for the measure theory live stream. I think it's pretty solid performance by live stream standard, and it has shown what's that? It has shown no signs of slowing down. Like, I'm pretty amazed by it. Okay. And guess what? This is funny. Hang on, let me just show you something. I mean, it's not fair because it's still too early. I uploaded this video today. Guys, can you see this page right now? This is my YouTube studio, by the way. I uploaded the complex number video, I squared minus 1 demystified, namely the definition of complex numbers. And I know, okay, this is a difficult topic to make. This is a difficult topic to make a video about. Why? Because most of my viewers already know complex numbers. But to do a complex analysis series, you cannot start one without defining complex numbers. So I'm always struggling. I'm in this writer's block of how to introduce the topic, right? Because if I'm just sitting here walking through computations of complex numbers, it's going to be pretty boring. So what I did is I started from like a historical perspective, right? How did complex numbers become unavoidable, and then it was even in that case it was viewed with suspicion, and how algebra and geometry played the role
in the development of complex numbers. So it was a mainly a sort of a genealogical study on how complex numbers develop to this day. I try to bring up things. I try to sort of say bring into things that perhaps are not so familiar by most people, but I mean by some people. For example, here I included the derivation, a sketch of derivation of the cubic equation, which turns out to be the impetus of studies on complex analysis. Sorry, not complex analysis, but complex numbers. And also there's a derivation of Euler's formula, the good old e to the I theta Euler's formula, in a perhaps a non-standard way. The typical way to derive that is to use Taylor expansion. I think there's more elementary ways to arrive at, so there's that. And also you can think of complex numbers in different models. Perhaps that's not always well known. So, I mean, well known by mathematical literature standard. I'm talking about well known by YouTube standard. For example, complex numbers can be thought of as matrices, and polynomial congruence classes. So overall, I mean, I spent, of course, quite a lot of time on this. But, well, as I mentioned in the very announcement of this series, complex analysis series, I don't really care how many views I get from this series. I don't really care about how, because the reason I decided to make it is purely for my own sake. If there are people who find this interesting, that would be great. But the main reason I decided to make the complex variable series is to rekindle my sense of wonder when I took complex variables. I was so in love with complex variables. The contrast was so severe that I took complex and real analysis together in the same semester. I hated real analysis, but I absolutely adored complex analysis. Yeah. So that was the motivation for this video. It turns out to be pretty long, over twice as long as my usual video. So I try to keep my videos under 20 minutes, and I think that is a sweet spot. But I don't want it to break the definition of complex number into several videos. I think it destroys the continuity of the lineage of thought. It's just purely the definition of complex numbers. You see, so that's the thing between so say, receiving information and understanding a subject. Right? That's the difference between, if you just wanted to present the definition of complex numbers and give some examples, then it will be done within 5 minutes. But where's the fun in that, right? Because the intellectual labor that went into understanding complex numbers is very phenomenal. Right? It's spanned over 3 centuries. But of course, this is nothing compared to the intellectual labor that went into understanding the real numbers. The real numbers are much, much harder than complex numbers. If you assume the real numbers, complex numbers are actually super easy. So that's why I always advocate, just in my personal opinion, that linear algebra should be taught. Linear algebra should be taught in the context of CN right from the start. Linear algebra should be taught, because, of course, there are special cases in real vector spaces that, for example, let's take a look at Axler. Okay, what I'm trying to say is, take a look at the content in Axler. Rn and Cn. Pretty much everything is either Cn and Rn both, or Cn first, then Rn. Okay. Operator in linear product space. This is in Cn, by the way. This is in Cn. Not Cn, but complex vector spaces. Complex vector spaces. So the vector space whose underlying scalars is complex numbers. So, see, operators on complex vector spaces are taught first. and then you talk about specific unreal, I guess. Is that how it's done? Is there a separate section on real? Huh. No, it doesn't. I thought there is. I thought there is. Because um, I remember for the most part of Axler, you only do complex and then specialize to real if you want to. So, yeah, I was trying, that is my point of view. You should keep things in complex. Whenever you need to specialize, then do it that way. Because it saves you from the hurdle of saying, of things like, oh, it's a polynomial, but it doesn't have a real root. Right. Okay. Anyway, let's come back to applied linear algebra. So where should we dive in? I think it would be, I mean, based on the level of the audience, I think it would be kind of boring if you start from the very beginning. And typically that's not how math books are read anyway. Right? Especially you don't, if you're not starting a subject from scratch, you would probably start from the middle. Are these sessions part of your course on university or are they a side of it? What do you mean by my course in university? I'm not in university anymore. These sessions, well, Wendell, right now my streaming sessions are organized as follows, the tentative plan anyway. I have 3 streams per week from this point. I try to do 3 streams per week. 2 have fixed topic. Tuesdays on measure series, Sundays on mathematical statistics and ballistics. I know, right? And Saturday is per viewer request. So today's is per viewer request. Okay, it's on linear algebra. And next week is on finance. I saw you're a professor. No, I'm not. I'm not a prof. I'm not a professor. Okay. I don't have a PhD. I just have a master's degree. So that's why, I mean, life happens and whatnot. But regardless, doesn't matter if I'm in academia or not. I'm always doing math, and as you can probably tell, spending quite significant time on it. Okay, so here we have. Let's. Do you guys? Can we have? You play on. You play one on TV. I play one on. You mean I play the role of a professor on TV? You mean on YouTube? I never claimed to be a prof. Okay. And I'm not one. Okay. I don't know why do you have the idea of play one. Perhaps because of my tone and whatnot, implying that I'm a prof. I don't know. It's just the usual way I speak. Okay. When I talk about math and whatnot. Okay. So here, what do you guys want to see? What do you guys want to see? Do you guys want to perhaps see least squares? You know, the idea is we start from a random chapter of interest and see how far we can go. Right? And see how far we can. If we run into things that we don't understand, of course we go back. And wriggle, you were talking about control the other day, right? So why don't we look at things like control, optimal control? And actually, you know what? So this is my schedule, okay? Streaming schedule. Today is the 4th. Tomorrow is the 5th. We will be doing mathematical statistics and ballistics. 7th, that's Tuesday, so that's measure theory. 11th is on finance, per viewer request. And 12th is Sunday, so that's mathematical statistics and ballistics again. 14th is on measure theory. So why don't we have a stream on optimal control and calculus of variation on the 18th? Okay, I'll schedule that as soon as possible if you like the idea. All right, so let's just look at control. Let's see how far we can go, starting from page 314. Okay. Is this regression? No. I mean, I don't know. Actually, I don't know. There's a huge part of the book that talks about regression. Okay, great. That's it. So 18s would be 18s would be the stream on optimal control, calculus of variation, and perhaps optimal. Actually, optimal control and perhaps some calculus of variation in general, because you cannot discuss optimal control without some background in calculus of variation. Okay, this will be very exciting because that's the mathematics of the space age, optimal control. It is a subject that is pretty much developed from scratch after World War II. Control. Okay, what do we mean by control in this context? You do a lot for your learners and you profess many things. Maybe you're not professor, definitely professor. Okay. Yeah, I mean, thank you very much, Rigo. I guess my goal is to build a community of people who likes math and just things like that in general. So as I always say on the Discord and on the channel, perhaps I'm not saying that enough because there's still confusion about my stance. Because I always say I consider my viewers my intellectual peers, and this is not. And this is really a fact that is backed up by YouTube statistics. Let's just put it that way. Okay, most of my viewers are of the same age as me. Same, and based on the comments, very similar education background. So, you guys are peers of mine. Okay? I'm just here to, perhaps I started a conversation, and I'm so glad that so many people can join. Okay, here, let's try to understand what we mean by control in section 15.2. Can you tell me the title of this book? Yeah, right here. Introduction to Applied Linear Algebra. Vectors, matrices, and least squares. So this book is quite unique, in my opinion, because it is a book on linear algebra that is heavily focused towards, so to say. It does cover the fundamentals, but it is a preparation for applications of linear algebra in optimization. Because linear algebra is used in so many areas, right? It's difficult to, of course, it's impossible, I think, to cover all of the applied topics, or at least all of the fields of applied topics in their fundamentals. It's just impossible. As you can see, the book, as I was mentioning, as I mentioned, part 1 is vectors, part 2 is matrices. So all of them constitute less than half of the book, and the entire third part is on least squares. So if you just take a snippet and ask yourself, okay, what is the title of the book? You might think, okay, well, this is perhaps statistics, machine learning, optimization, but no, this is actually a linear algebra book. Yeah, so I'm going to continue on 15.2. What does control mean in this setting? In control applications, the goal is to decide on a set of actions or inputs specified by an n vector, x, that achieve some goals. Okay, so that's pretty high-level description. The action results in some outputs or effects given by an m vector y. Okay, so this is actually very high level. right? It seems like you have a black box. X in Rn in, Y in Rm out. Sort of an input-output model. Okay, we consider here the case when the inputs and outputs are related by an affine model. Okay, so that's pretty standard and perhaps easy to manipulate, right? Y equals ax plus b. The m by n matrix A and the m vector B, okay, you have A and B. These two are constants. Characterizes the input-output mapping of the system. Make sense? The output parameters A and B are found from analytical models, experiments, computer simulations, or to fit past observed data. Typically, the input or action x equals 0 has some special meaning. So that's the system without any sort of input. The laissez-faire, if we borrow economic terms. If you put no input into the system, what do you get? You get B, right? The B vector gives the output when the input is 0. Oh, somebody's playing video game. That's my friend. In many cases, the vector x and y represent the deviation of the input and output from the standard values. Yeah, the do-nothing case, exactly. So, okay, what do we want? So we have our model. So we have our y equals ax plus b. Let's put that in our notes. Okay, so this is control. What do we mean by control here? Apply linear algebra. Y equals ax plus b. Okay, this is our black box. X is in Rn. Okay, Y is in Rm. Okay, so what do we want? We typically have a desire or target output denoted by desired, okay, or denoted by the m vector, y desired. Think of a thermostat. Right? This is the temperature you set for your AC. The primary objective is J1. I guess you want to minimize that. The norm squared deviation of the output from the desired output. You want to minimize that. The main objective is to choose an action x so that the output is as close as possible to the desired value. Is as close as possible. Okay, there are many possible secondary objectives. Okay, well, there's secondary objectives. The simplest one is the norm squared of the input. J equals x norm squared. So the problem is to optimally trade off the missing target output measured by y minus y desired norm squared. So basically this is y minus y desired, right? Norm squared. So you want to minimize that. The less, the better. The lower, the better, right? And also J2, we want to minimize that too. But so we want to trade off the missing target output and keeping the input small. Okay, so that's the secondary objective. So how do we combine them? We don't know yet. Another common secondary objective has the form J2 equals not the norm of x per se, but rather x minus x norm. Perhaps this is nominal, okay, nominal. nominal, x nominal, where x nom is the nominal or standard value of the input. In this case, the secondary objective is to keep the input close to the nominal value. This objective is sometimes used when x represents a new choice. X is a new choice from the input, and x norm is the current value. In this case, the goal is to get the output near its target while not changing the input much from its current value. Okay, that makes sense. So let's write down the objective functions. Okay, so you have the primary objective. You want to minimize the square norm of y minus y desired. Okay, primary objective. Secondary objective, want to minimize. You always minimize, so let's just remove that. Just say this is J1. J2 is x norm squared, or x minus x nominal square, norm square. Okay, so because we're in part 3, remember? They're all least squares. They're all least square problems. Okay, so examples. Control of heating and cooling. Is that like thermostat? Let's see. As an example, x could give the vector of n heating or cooling power levels in a commercial building with n air handling units, perhaps AC, with xi greater than 0 meaning heating and xi less than 0 meaning cooling. Okay, and y could represent the resulting temperature at m locations in the building. I see. So imagine if you have m rooms or m floors, and you can have n AC units or heating units inside the building. So that's the interpretation. The matrix A captures the effect of each of the n heating and cooling units on the temperatures in the building at each of the m locations. The vector B, so the vector B gives the temperature at the m locations when no heating or cooling is applied. That's cool. Or that's hot. Anyway, the desired or target output might be, so here you're treating the desired temperature as uniform. So you want the temperature to be the same at all locations, but it doesn't have to. It doesn't have to. So of course, it's a choice, not a particularly special choice, assuming the target temperature is the same at all locations. The primary objective, y minus y desired square norm, is the sum of the squares of deviation of the location temperature from the target temperature. Okay, that makes sense. The secondary objective, J equals x norm squared, is the norm square of the vectors of heating, cooling powers. Okay. I don't know what x stands for. Okay, y is temperature, so we know that's a physical quantity. I don't know what x is. Is the I'm not sure. Okay, so I don't know what xi is. Some sort of measurement for the energy you use, I guess. Immediately start overthinking this. The vector B could be drift with time without any heating or cooling. Exactly, you're right. Here we're not considering a time-dependent model. Right? If you're adding time into the equation, then you would have some sort of differential equation, like the Newton's law of cooling, to describe the evolution of temperature. And which, by the way, is exactly what optimal control theory is about, right? You have an underlying dynamical system. Here we don't have a dynamical system, okay? Just assume constant temperatures, constant constant ambient temperature if you want. The atmosphere stays the same temperature. So this way, if you don't heat or cool it, it will just be the same as the atmospheric temperature. Duty cycle of the ice heat pump is what? Yeah, yeah, that makes sense. That makes sense. All right, so the secondary objective, J2, equals x norm squared. The norm squared of the vectors of heating and cooling powers would be reasonable, since at least roughly related to the energy cost of heating and cooling. Right. We'll suspend thermodynamic display. Exactly. I mean, we want to get the main idea right. Not the physical realism is not particularly important in this example. Okay. All right. So we find tentative choices of the input by minimizing J1 plus lambda J2 for various values of lambda 2. Okay. So that's a way to combine the objectives. As I was saying, right, from this section of the text, it's not clear what your priorities are. I mean, it just says verbally that J1 is the primary objective. So it seems like we're combining them through a linear combination. Perhaps combine through J1 plus lambda 2, J2. This is one way to combine the objectives. Okay? So let's keep going. So here, lambda 2 is a parameter of choice. It's a parameter of choice. It's not, I guess you can, for example, here if J2 is the heating and cooling powers, you can put J2 as the energy cost, I suppose. I was just thinking about this, how to encode which constraint is most important, right? You would tweak the parameters. You tweak parameters. Actually, on going off on a side tangent, in statistics, there is something called regularization, or in machine learning, there's something called regularization. This is very similar to regularization in statistics and machine learning, right? Because sometimes you want to penalize the complexity of a model, so this way you don't overfit. Right? So basically, if you take J1 to be this, okay, if you take J1 to be what's stated here, and J2 to be x norm squared, in the context of statistics, this would be called a ridge regression. Ridge, this is how you spell it, ridge regression. Also known as Tikhonov regularization. Regularization. Same thing. Okay. Because sometimes if you don't control the size of your input, you might get wildly unexpected behavior in the fitted model. So and that's just in the context of statistics. Here we actually do want to minimize square norm of x for physical reasons. Okay, it says if for the current value of lambda 2, the heating and cooling powers are larger than we like, we increase lambda to recompute x hat. Why increase? Why do you increase that? The current value of lambda 2, if for the current value of lambda 2, so let's say lambda 2 is given, and the heating cooling powers, I think you're talking about J2, right? Heating cooling power would be J2. If J2 is larger than we like, we increase lambda 2. So this way, lambda 2, if lambda 2 is increased, then J2 is more important. Gains importance, you can just put it. I'm not saying it's more important than J1, but at least increase J2, increase lambda 2 increases the importance of J2. So this way, perhaps, so this, I mean, it's not a theorem, but perhaps this way will give us X that minimizes J2 even further, I suppose. I've been starting at that too. I think they meant decrease, but like lambda 2 is the inverse of the cost of powering. I think this is just a rule of thumb. Okay, let's put a note on that. What it's saying is that there's a remark which we are unsure of. It says pick J2 equals x norm squared. Pick that. If the argument of J1 plus lambda to J2, if the argument is higher, no, this makes no sense because argument is a vector. How can that be higher? Okay, let's try to formalize things a little bit. Say, let's call this x of lambda 2. This depends on lambda 2. Yeah, I think I'm getting our intuition. So x of lambda 2 is the argument of J1 plus J2 plus lambda 2 J2. Okay, so this is our x2. It says if J2 evaluated at x of lambda 2 is higher than we like, quote unquote, then decrease lambda 2, actually increase lambda 2. I think it makes sense. Wriggle? I think it makes sense because let's consider the extreme case where lambda 2 is infinite or next to infinite. So this way, J1 almost does not matter. If J1 does not matter, you're essentially just minimizing J2. And when is J2 minimized? Well, x equals 0. So basically, we can already see the intuition is, right, lambda 2 approaches infinity implies, will lead to x of lambda 2 approaches 0. So this way, if you change put lambda bigger, your x will get smaller, will be closer to 0, so J2 decreases. Right. So if J2 is bigger than we like, we increase lambda 2, so this makes sense. Okay. Okay. I think this is a very satisfying way to read a book. Let's say if you just, increase lambda 2. I don't know what's really the reason behind that, but you just take that for granted. I mean, that's like a last resort. If you really still can't figure it out, then you put a note on it and not stall the progress, right? But it's actually these little habits of pausing and think about why that makes absorbing information so much faster, actually. Okay, so that's one example. That's one example. Here you have another example. I guess it's an economic model, but I just want to get into the math. Like, how do you do this? How do you do the math? How do you do that? I guess you can apply the least square algorithms earlier. It's just a this is this just oh okay, that's just a different bunch of examples, huh? This is just a bunch of examples. Okay. I think having one example as motivation is suffices for most learning. But of course, it's helpful to think about more applications later. But here, let's just try to figure out what we mean, or not, no, what do we mean? What's the machinery to do this sort of optimization? Let's go back. Least squares. Least squares. Okay. Least square. And this is a beautiful application of linear algebra. My middle name is heuristics. Okay. In this chapter, we look at the powerful idea of finding approximate solutions of overdetermined systems of linear equations by minimizing the sum of squares of errors in the equation. The method and some extensions we describe in later chapters are widely used in many applications areas. It was discovered independently by Gauss and Legendre. Well, Gauss was an asshole about it, but anyway, that's unfortunate, but let's move on. Least square problem. Suppose that the M times N matrix A is tall. A looks like this. M times N matrix is tall. So it means M is much larger than N. So for the system of equation AX equals B, where B is an M vector, it is overdetermined. Basically, you have way more equations than your unknowns. Right. So these equations have a solution only if B is a linear combination of columns of A, which is practically impossible. For most choices of B, however, there is no n vector x for which AX equals B. As a compromise, we seek for an x for which R equals AX minus B, which we call the residual of the equation, as small as possible. This suggests that we should choose x as to minimize the norm of the residual AX minus B. Right? So that's basically the idea of a least square. Remember, as we stated earlier in the earlier part of the stream, AX is a linear combination of columns of A. So what we have here is, okay, A is M by N matrix, M by N matrix. So consider the ambient space Rm. The column space of A is a subspace. So B is an arbitrary vector in Rm. It doesn't have to be in the column space of A. So this is B. This is B. So we know that AX lies in column space of A. So we just try to minimize the distance. And how do you do that? You do the orthogonal projection. And that's least squared geometrically speaking. Okay, so that's it. The point that minimizes the distance is the orthogonal projection. If we find an x for which the residual vector is small, we have AX approximately equal to B. X almost satisfies the equation. Some authors use the residual as B minus AX, which doesn't matter. Minimizing the norm of the residual and its square are the same. So we can just as well minimize the square norm. So the problem of finding n vector x hat that minimizes AX minus B, norm squared, over all possible choices of x is called the least square problem. It's denoted using the notation minimize AX minus B length squared, where we should specify that the variable is x, meaning that we should choose x. The matrix A and B are called the data for the problem. They're given, which means that they're given to us when we are asked to choose x. The quantity to be minimized is called the objective function, or just objective, of the least square problem. The problem 12.1 is sometimes called linear least squares to emphasize that the residual. So what do we mean by least square, linear least square? The linear least square problem is the residual, the norm we are trying to minimize is an affine function of x. And to distinguish it from nonlinear least square problems, which we allow the residual r to be an arbitrary function of x. So that's why the problem linear regression can sometimes be a little bit confusing. Under this definition, linear least square problems, polynomial fitting is also a linear least square problem, because polynomial, if you're using a polynomial to fit a data like a parabola, okay, pt is a0 plus a1t plus a2t squared. This is linear in the coefficient. This is linear in the coefficient. If you want to fit a parabola, you would need the coefficient. Does the book implicitly assume the two norm? Exactly. Yes, it does. Here, it's explicit. It's the two norm. And of course, this is least square after all, so everything is in two norm. The entire part 3, I believe the entire part 3 uses two norm. Okay. If you use, say, the one norm, much of the machinery falls apart. But still, like one norm is interesting on its own, and also a linear algebra problem. It'll be linear programming, not least squares. All right. So here we have interpretation, right? So we can have different interpretations of the same least square problem. But I just keep reading. So here we will study the nonlinear least square problem in chapter 18. Any vector x that satisfies this inequality is for all x is a solution of the least square problems. So that's a solution. Such a vector is called the least square approximate solution of ax equals b. It is very important to understand that a least square approximate solution x hat of ax equals b need not to satisfy the equation ax hat equals b, of course, right? Because this is not the problem we're solving. X hat is not, from the get-go, not assumed to be a solution of ax equals b, because we know in general ax equals b is simply unsatisfiable. Okay, so some authors use the confusing phrase x hat solves ax equals b in the least square sense, but we emphasize that a least square approximation solution does not in general solve the equation ax equals b. Yeah. If the norm of ax hat minus b is small, then we can say x hat approximately solved. That's, I mean, the language is vague enough that it's hard to attack. Okay. On the other hand, there is an n vector x that satisfies ax equals b if there exists. Okay, if the equation can be satisfied exactly, then this is a solution of the least square problem, because in that case the residual is 0. Of course, that's minimized. Associated residual norm is minimized. Another name for least square problem is called regression. Typically in statistical data fitting problems, it's called regression. Linear regression, nonlinear regression, it usually uses some sort of least square algorithm. We say that x hat is a solution to the least square problem as a result of regressing the vector b into the columns of A. Regression. Text is quite digestible. Scrolling the PDF right now. Yeah. Exactly. So this is, I think it's very friendly. It's written in a very friendly manner. Okay. Good tone of voice. Yeah, it's pretty much, I think it's very anti-Bourbachian, if you can put it that way. I enjoy both styles for obviously different reasons. But I think it's a good balance we should try to keep on the channel, because I did linear algebra done right streams before. It's only fair to present some of the application aspect. So this way we have a good balance of both. So, okay, column interpretation of the least square problem. If the columns of A are m vectors, A1 all the way to AN, then the least square problem is a problem of finding a linear combination of columns that is close to the m vector. That's the picture I was drawing. A linear combination of the column, of course, lies in the column space. You're just trying to find a linear combination of column that is closest to B, which reduces to an orthogonal projection problem. Right, so that's it. So if x hat is a solution of the least square problem, the vector ax hat is closest to B. Exactly. This is a least square problem, which is equivalent to orthogonal projection. All right. So, row interpretation. So this is a row interpretation. If you do a row interpretation, this is visually the same as what you've typically seen in linear regression textbooks. So you're trying to draw a least square line so that the residual sum of squares is minimized. So that's the row picture. Now, I find the column picture to be much more powerful than this because these little distances can be hard to interpret. Okay. But basically that's the row interpretation. Each residual is given this way. So the least square problem is then this one. The sum of the squares of the residual is m scalar linear equation. In m scalar linear equation, minimizing the sum of squares of the residual is a reasonable compromise if our goal is to choose x so that all of them are small. All right, makes sense. Okay, so now you have an actual example. Solving this is quite easy. You want to minimize ax minus b norm squared. So let's draw the picture here. Draw the 3D picture. What's the column space of A? Well, let's draw the column vectors first. 2, minus 1, 0. So this is x1, no, not x1, but rather, how should I name these coordinates? Just call it xi, okay? Xi1, xi2, xi, eta, and zeta. Okay, how do you write zeta? My goodness. You just write alpha, beta, gamma. Alpha, beta, gamma. Okay. As you can probably tell, I'm not a researcher in Riemann zeta function. I pretty much never use that letter. Well, I do typeset it, but I rarely write it. Okay. Here we have the first column vector 2, minus 1, 0. 2, minus 1, 0. So it's here. First coordinate is 2, alpha is 2, beta is minus 1, gamma 0. Okay. And then you have 0, 1, 2. 0, 1, 2 is here. So the column space of A is a plane that is spanned by these two vectors. So that's the column space of A. By the way, do not do this. Do not do what I just did in your notes or in your books. This is horrible practice. Do not do this. Do it on your notebook or scratch paper. They exist for a reason. B is 1, 0, minus 1. 1, 0, minus 1. So it's down here. 1, 0, minus 1. So you want to project that onto the plane, basically. And if you spell out the objective function, you get this. Right, so solving, it just says, okay, so it just says using the method in the next section or simple calculus. Right, so to solve this minimization problem, of course, you can use calculus, take the derivative equals 0. Right. But there's a much better method without calculus. I mean, they're equivalent, but more geometrically meaningful. So imagine if we go back to the original setting. Right, so we want b minus ax, as you mentioned, to be perpendicular to the column of A. What's perpendicular? Well, dot product equals 0. So if you take a column in A, so this is what A looks like. So the columns of A are C1 all the way to Cn, Cm, so to say. What does the column space perpendicular to B minus AX mean? Well, that means the dot product for each column, the dot product between itself and B minus AX, namely the residual, is 0. Orthogonal projection of B onto the plane, exactly, this is the picture. Right? So we want to express that algebraically. Orthogonality means dot product 0. So take one column and dot product with the residual gives you 0. And in fact, all of the columns should have that property. Right? So let's say Ci dot with B minus AX equals 0. But what's dot product? Dot product is transpose. It's just a trick to write dot product. A transpose Ci transpose B minus AX equals 0. And this works for all the columns of A. So that must mean A transpose B minus AX equals 0. So this is called the normal equation. This is called the normal equation in statistics. Normal in the sense of a normal vector. Because literally, the residual is a normal vector of the column space. Normal means perpendicular, okay? Not normal distribution or average or regular, that sort of thing. Okay, normal has a geometric meaning. Normal equation means perpendicular. And of course, symbolically, you can give an explicit solution, which is useful for problem with small sizes. So you have A transpose B equals A transpose A x. So x is, sorry, not, yeah, x is, assuming A transpose A is invertible. Okay, this happens when A has full rank. Because A has full rank means the rank of A equals the minimum of m and n. So basically that's the full rank. So if you have a very tall matrix like A here, that just means the rank of A is n. So all the columns are linearly independent. So that's the full rank assumption. If A is full rank, then A transpose A is invertible. So you can write your solution X this way. So it has a closed form formula. However, for practical computation, we don't usually do this because calculating inverse matrices are expensive. Okay, so we don't usually do that. Instead, you would use something like a QR algorithm, QR decomposition of A to do this. But this closed form formula is useful in statistics for derivation purposes. You can calculate things like sampling distributions from this closed form formula. So it can be helpful. Okay, so that's the linear algebra way, okay, without differentiation. Okay, but basically that's the answer here. So here's the solution. In this section, we derive several expressions of the solution of the least square problem under one assumption of the data matrix A. The columns of A are linearly independent. That's the full rank assumption I was talking about. A has full rank. Okay, and then you can plot the contour of the objective function. And its contour should be an ellipsoid. It might not be straight in the sense that its axes are exactly the same as coordinate axes. It doesn't have to. But it should be an ellipsoid because the objective function is positive definite. Okay, simply because the objective functions are positive definite. All right. Solution via calculus. Solution via calculus gives you the gradient formula. The gradient, this formula can be derived from the chain rule given on the page 184. Actually, this might be a good topic that we discuss sometime, is the calculus of matrix and vector value functions, which is quite useful in machine learning, but typically not covered in linear algebra courses. Matrix calculus. I think this is matrix calculus stuff. 184. So, okay, chain rule. This is the usual chain rule, classic chain rule from multivariable calculus. Of course, to discuss chain rule, we're talking about a composition of two functions. Suppose you have f and g that are differentiable. F is from Rp to Rm, g is from Rn to Rp. So clearly, you would first evaluate g, and then you get an Rp vector, and then you feed that output into f. So H is the composition of f and g. Okay, and then you do the usual chain rule. And it can be written as a matrix multiplication formula. Okay. So that's the chain rule. So how do we, hang on, how do we, okay, when f is a scalar value function, the derivative matrix are transpose of gradients. Derivative. That's why, because gradients are typically viewed as column vectors in multivariable calculus, which really should be row vectors. Okay, gradients really should be row vectors because row vectors correspond to linear functionals, and column vectors represent vectors. As physicists like to call them vectors and covectors. So here, yeah. So if, in particular, if gx is affine, oh, by the way, sorry, we didn't finish. The gradient of h of x is dg transpose times the gradient of f of g of x. In particular, if g of x is affine, then d of g is just a. Actually, a transpose. D of g is a, and then transpose, you get a transpose. And then the gradient of f of ax, az plus b. So let's use this rule here. Differentiation formula. Which says h equals f of ax plus b. Then the gradient of h. So basically, x, as we mentioned, x is in ax plus b. F is what? F takes values in Rm. No, we're talking about G. G is from this RP. Okay? So you have a vector Rn maps into Rp, and then use the f function to map that into Rm. So that's the order here. So what's the gradient of G? The gradient of G is the gradient of H. Gradient of H is A transpose. The gradient of F evaluated at AZ plus B. I'll stay for another 20 minutes and we will finish the stream. All right, so that's the differentiation formula. And now let's apply this to least square. Okay, what's the least square objective? Least square objective J of x is ax minus b, normed square. Okay, so this means our f here f of x is just the square norm function. What's the gradient of that? Well, it's simple. It's just x1 squared plus all the way to xn squared. You can easily calculate the gradient. The gradient comprises of a vector whose components are partial derivatives. So df over dx1 all the way to df over dxn transpose. So that's just 2x1 all the way to 2xn transpose. So it's just 2 times x vector itself. So therefore, we write the gradient of x norm squared equals 2x. Notice this is analogous to derivative of x squared is 2x. Okay. Kind of similar. Okay, so this is for our f, and therefore we have the gradient of j of x is A transpose. The gradient of f evaluated at ax minus b. But we know that the gradient of f is 2x, so it's 2 times ax minus b. So that's the calculus solution. See, this is the calculus solution. Going back to least square. Here, the gradient derived. Okay, for completeness, we'll derive the formula 12.3 from scratch here. Okay, this is a differentiation steps using no known results, but we can skip that. Okay, so now if you set it to 0, you get the normal equation. But here, as you can see, it would be better if we simply, I mean, for computational purpose, you have to rearrange as such. But for geometric intuition, A transpose AX hat minus B is perhaps the most transparent version. Without the 2, okay? Without the 2, A transpose times AX hat minus B is perhaps the most transparent version. It literally says the residual vector is orthogonal to the column space of A. AX hat minus B is the residual vector. It is orthogonal to the column space of A. So that's why it's called normal equations. The coefficient matrix A transpose A is the Gram matrix associated with A, so-called Gram matrix. Its entries are inner products of columns of A. Let's just quickly verify that. A transpose A. So suppose A has columns, has n columns. So is that A1 all the way to AN? These are columns. So A transpose looks like A1 transpose all the way to AN transpose. Multiply this by A1 all the way to AN. You indeed have a matrix of this form: A1 transpose A1, A1 transpose A2, and all the way to A1 transpose AN. Down here you have AN transpose A1 all the way to AN transpose A2 all the way to AN transpose AN. So basically, A transpose A looks like AI transpose AJ, which is exactly the dot product between AI and AJ. So that's it. That's the Gram matrix. That's why its entries are inner products of columns of A. Okay, so now if we, given that our assumption, the columns of A are linearly independent, implies that the Gram matrix is invertible. And that's a basic result. Can we prove that real quick? It would be interesting to prove that. So suppose A columns are linearly independent. Suppose that. Prove A transpose A is invertible. How do we do that? It's a good exercise in my opinion. How do we prove that? Well, let's do it this way. Okay, let's start in our notes. Exercise. Assume A A has full rank. A has full rank. Then prove A transpose A is invertible. So A has full rank has two situations. It either has a linearly independent linearly independent columns or linearly independent rows. Okay. For least square problems, because the number of rows are much greater than the number of columns, full rank just means linear independence of columns. So let's just assume A has linear independent columns. Let's pick this assumption and prove A transpose A is invertible. The technique should be quite similar for assuming linear independent columns and linear independent rows. Okay, so the technique should be quite similar. Okay, to prove A transpose A is invertible, to do that, we can assume, suppose A transpose A x equals 0. You need to show x is 0. So that's a theorem from basic linear algebra. If a square matrix is invertible, then the homogeneous linear equation must only have 0 solution. Right? X equals 0 is always a solution. The special thing about invertible matrices is that the homogeneous system only has 0 solution. So we suppose A transpose A, x equals 0, we need to show x is 0. If that's done, then then the matrix is invertible. Okay. All right. So A transpose AX equals 0. Can we have AX equals 0? Because if here we assume that A has linearly independent columns, right? Linearly independent columns, AX is a linear combination of the columns of A. If that equals 0, then X must equal 0. So it suffices to, let's write, since A has linear independent columns, it suffices to show AX equals 0. If AX equals 0, then X must 0. So how do we show AX equals 0 then? Well, let's use a little trick. Let's consider the length of AX. Length squared of AX. The length squared of AX is X transpose A transpose AX. But this is just 0. So you just get 0. And we're done. I think this is one of the quizzes I gave on the channel just a few days ago. Let me see how well people did. Shall we? Hang on. Yeah. By the way, yeah. Let me just. You can in the last few minutes. Let's just take a look at the quiz's result. Hang on. Guys, let's take a look at the results I gave for the quizzes. Okay. So this is a quiz I did for today. 47 correct. 47%. Um, let me guys know. Let me guys sorry. Let I want you to guys to comment on these results and tell me which ones are the most common mistakes. Okay. I wanted to perhaps keep the records on the side so we can do a little bit of a recording too. Okay, so the first question I wanted to just wanted to write down the solution here to separate things a little bit. Just briefly remark on these exercises I posted in my community tab. The first one says FA union B equals FA union FB. Union FB. Okay, so that's the first equation, which I outline the proof in the explanation. Hang on. I'm proud I have stuck around the whole time and not having attention to him, but man, you're a killer checking for 4 hours. Thank you very much, Rigo. Thanks for staying. So basically, this is a rare occasion that images actually behave well. The moral of the story is inverse images behave much better than images. So actually FA union B equals FA union FB. This is an anomaly. This is an anomaly as far as the images is concerned. Typically, you don't have these nice equalities. However, the inverse image is extremely well behaved. The second identity is not an anomaly. The second equation is not an anomaly. Actually, you know what? Let's prove the second equation. The relationship between inverse images. And actually, this will play a role in measure theory because measure theory uses a lot of inverse images. So I proved here an explanation of the first equation of one direction of the first equation. So proofs 1. This direction is proved in the explanation. And the reverse direction is quite straightforward. So let Y be in FA union FB. So you have two cases. So when we write cases in proofs, we want to make sure that the cases are mutually exclusive. So case 1 is Y in FA. So case 2 must be Y not in FA. That's case 2. So there seems to be a common mistake in proof writing. Say case 1, Y is in FA. Case 2, Y is in FB. Of course, if Y is not in FB, Y is not in FA, then Y must be in FB. But starting your case with Y in FA, Y in FB is not a good practice. When we do cases, the cases have to be mutually exclusive. You don't want the cases to have overlaps. Inverse image behavior is actually a deep concept. I didn't know that actually. I thought it was just something that's nice, but I didn't really dive into it. Yeah, if you can enlighten me on this subject, I will be more than interested to take a look. Because I was, that's so weird, huh? This just somehow inverse image behave
better than images. I don't know why, but well, I take it. This is that kind of deal. But yeah, let's just finish this proof. This is a nice little thing we try to pay attention, okay, when we do proof writing. Sometimes we want cases in the proof. Make sure the cases are mutually exclusive. So y is in FA, that's the first case. Case 2 will be y not in FA. Now, no overlapping cases. That's exactly. You don't want to write case 1 y is in FA, case 2 y is in FB. That's not a good way to write things. Of course, when y is not in FA, y must be in FB, and then you can do your deduction as usual. But it's just good stylistic choice, because sometimes when you check your proofs, you don't want to check whether these two proofs has overlapping scenarios. That's just not a extra mental toll on the reader. Case 1, y is in FA. Well, y is in FA, what this just means f of x equals a. F of x equals y for some x in A. Definition of image. Then x is also in A union B, and therefore y is in f of A union B. Okay, and the second case would be similar. Y is in FB, so y equals f of x for some x in B. For some x in B, so therefore you get y is x is in A union B again, y is in f of A union B. Okay, so part 2, inverse image behaves well. F inverse of C union D. C union D, I'm just going to do one direction, is contained in the union of F inverse C union F inverse D. So you see, what I'm trying to say is the inverse image always distribute with the union, intersection, all of those things, and also complements. It behaves extremely well, but not so well with images. This is an anomaly. For correspondence, ideals, and express localization images can save the day, or making a variety of singular. I have no idea. Is that some sort? Is that abstract algebra? Because my algebra background is extremely weak, actually. So yeah, for me, the fact that inverse images behave well is just a fun fact. Okay, but yeah, Dezen, please let me know which area of mathematics is this abstract algebra or category theory, or I don't know, logic. Please let me know. So yeah, this is rather basic, but let's just walk through it. Let x in the pre-image, consider x to be in the pre-image or inverse image of C union D. This just means f of x is in C union D. F of x is in C union D. Once again, you have two cases. Case 1, f of x is in C. Case 2, what did we just say? F of x not in C. Okay. If f of x is in C, well, x is in the f inverse of C, which is contained in f inverse of C union f inverse of D. Now, very straightforward. And second, you would have x, if f of x is not in f of then f of x is in D, and then you just proceed as usual. So yeah, this is a good lesson, in my opinion. The first one is a fluke. The second one is a standard. Okay. All right, so this statistical quiz turned out to be quite disastrous. I mean, once again, no judgment. The whole point is to have a low-stake environment to practice these concepts. Sampling without replacement from a finite population would result in non-independent data. Okay, this is very fundamental. Okay,
I should make a video about this because of the statistics. Okay, so which one I was talking about? A linear algebra quiz. You see, the results are typically around 50, but the bragging rights of being correct. You're talking about me? Um, I oh, well, I do have an ego, okay, but I'll try to suppress it. I'll pray to goodness. I pray to God to try to suppress my own ego because there's so many things I still don't understand. Okay, and here we have. I'm talking about a linear algebra question I made a few days ago, which also seemed to be kind of confusing. Yeah, right here. This is the one. No, for doing the low stake quizzes like me. Okay, so that's the question. It's a little bit different from the proof we did here. Right here we assume A has full rank. Prove A transpose A is invertible. I guess this is the same. It is the same exercise. It is the same exercise. Here we supposed A transpose AX equals 0, then AX equals 0. This is true. This is true regardless of A having full rank or not. See? This is true regardless of A having full rank or not. But if A has full rank, then from AX equals 0, you can derive X equals 0. So this is exactly the same question, and the proof is the same. I consider AX transpose. So not AX transpose, AX norm squared. AX norm squared. So AX norm squared equals 0 is an artifact of how inner product works. See, this is, it feels kind of weird, right? Somehow A transpose can be cancelled with no price, with no extra assumption. But this is really just an artifact of how inner product works. And my comment here is that this is crucial for singular value decomposition. Once again, this is to see details on this, go to the UWaterloo open math page. I'll just finish this and I'll end the stream. Here, linear algebra 2, go to application of orthogonal matrices, singular values, singular vectors, and singular values. Unfortunately, for linear algebra 2 part of the module, okay, it does not have many exercises. That's a little bit of a drawback. Okay, but the exposition is still excellent. All right, so here, this is the theorem I was talking about. The null space of A transpose A and null space of A are the same. One direction is trivial. The other direction is exactly the same proof it did in a little quiz. Okay, and then it turns out to be a cornerstone for singular value decomposition. Anyway, I'll stop the stream. Thank you very much for joining the stream, and I'll see you, if you can, tomorrow. Anyway, bye now.